So let's talk about this concurrent algorithm that I outlined. It was not really an algorithm; it was an outline. And how many of you read Chu's message on Piazza about the concurrency issue? Okay, so he pointed out his message indirectly or directly points out issues with this. Okay, so I said, look, a tree of message paths exists. Okay, create vector stamp and buffer for each leaf in the path. And when a message arrives, see if its vector timestamp is greater than one of the vector timestamps, put it in the buffer for that vector timestamp. Otherwise, create a new vector timestamp and buffer, and deliver the message after flagging concurrency. So there are some things that are wrong with this. Again, this was an outline, so if something is wrong, it's not really that wrong. Can you guys just, the way I've stated things, is there something? There's two things that I said that are not quite correct here. So what problem were you trying to solve with your successor function?
Successor function.
So what problem were you trying to solve?
Actually,
there is a problem here.
You mean find the successor?
Yeah, you gave a successor function in Piazza, right? Which is different from the successor function I gave in class.
So I just find whether there is only one component.
Yeah, I understand the function.
Yeah.
But what problem were you trying to solve? Were you just being lazy? You didn't want to create sorry?
Whether to deliver this character immediately.
So whether to deliver the concurrent message immediately or not. And what am I saying here? That when a new path is when a message along a new path is found, deliver the message immediately. But there may be some message before that that hasn't arrived. So I shouldn't deliver immediately. I should go in and figure that out somehow. Right? So this algorithm becomes a little tricky. Is it really a tree of message paths? No, in general. So you start with some states, diverge. Do you ever merge back, maybe? Yeah, you might have a site that receives two concurrent messages, processes them, and then delivers a new message in response to that. Okay? So that means we don't, and that's kind of what you were hinting when you want to just have one vector timestamp. That seems nicer because then my tree is not just getting unbounded, right? And I do some garbage collection at some point when I merge the parts. Okay. So so we have two problems. This is the DAG, okay, and does a DAG have leaves? Is that term, you guys who have done data structures recently? What are nodes with no outgoing edges called in a DAG? DAG, directed acyclic graph. Okay, a node can have multiple parents. A tree, a node can have only one parent. Okay, but what about a node that has only parents and no children? Can we call that a leaf? Is that or just a sink, pure sink? Okay, we have sources and sinks, and maybe that's a pure sink. You guys who've done, I did data structures before you guys were born, so Okay. Actually, I never really did data structures. I was a double E major, so I kind of learned that on my own. Okay. So this is not true, and we don't want to go and deliver the message immediately. Let's go and look at the DAG thing. So let's assume that there was an initial timestamp that was created, and then node 1 sent a message, and node 3 sent a message concurrently, right? And after node 1 sent a message, node 2 sent a message, right? And then some site received all of these messages and sent a message. Site 4 sent a message after receiving messages from all 3 sites. Okay, node 1, node 2, node 3, right? So we've converged now, and we want to do some garbage collection of our vector timestamps if you're going to have multiple timestamps. And the issue is that supposing at a site, this is a timestamp, right? And it receives this message without having received this message before. Okay. it should not deliver this message, as my previous slide said. Right? So it should wait for this message, but when this message arrives, it is not the successor of this message. It is a successor of some parent node of my vector timestamp. If I look at the derivation tree, this particular node is a parent of is a successor of a parent of mine, and not my successor. Okay, because it's a concurrent message. Okay, and that's what your successor message was trying to figure out. Is saying, is this the successor of my parent rather than my successor? Right? So rather than having, we said that look, some component of the new thing should be 1 plus some component of mine. 1 plus, not 2 plus. Okay, so I should not go and process this message when it arrives because 2 of these components are more than. Okay, so exactly 1 component should be exactly 1 more than one of my components, right? And what did you do here? Rather than equals for all other I, for all other j, for all j not equal to I had equals, and what did you do? Well, sorry, what did he do? Anybody else? Less than equal to, right? That's my parent. That shows that, because I must have incremented these values. That means these were at some point parent nodes of this particular node, timestamp node, right? So that was what. So this particular node is not my successor, so I have to go and modify my successor. And that successor function assumed everything causal. And now we are dealing with concurrency. So now we check if it's less than equal to. Yeah.
So how is that 1111 generated?
So 111 generated by some guy receiving a message, receiving these 2 timestamps and then sending another timestamp message. Node 4 receiving all 3 messages and saying, okay, here's my message now. Okay. So that's good. And I mean, you're really seeing research happen. This must have happened 20 years ago, but it's just to find that research. One of the reasons I joined computer science and not some other field was that I hated going to the library. I had an elder brother who always knew everything. Before Google, he was my Google. So I just never got the discipline of going to a library. So computer science was very young when I was young. And it's still young relatively, so you don't have to mine a lot of stuff. And now this stuff is so rich that to find somebody who's done this algorithm is a little hard. Anybody try to Google for concurrent timestamps? I haven't tried it. Okay, it's much more. You can just do it yourself, right? And find bugs and have the class then fix it. And in fact, operation transformation is a story of this, and that story I've seen unfold in my lifetime as a reviewer of various papers. Okay, a reader of various papers. So you still need to buffer messages along each path. Okay, I might receive a message here whose predecessor has not been found. I might receive a message here whose predecessor is not found. So I do need to buffer messages along multiple paths. Okay, and then the question becomes: are you going to have multiple buffers or a single buffer? Okay, and if you're going to have ordered buffers, like I suggested, then so you're going to have a DAG of message paths. Create buffer for each leaf in the DAG. I'm going to call it a leaf. A leaf is a node with only sources and no sinks. Okay, and when a message arrives, find one of these find a buffer, okay? And if a buffer already exists, okay, so I should have really asked you this question, but when a message arrives, you may already have a buffer for that, right? How do you find out if you already have a buffer? Don't read this. If there is already a buffer into which this message can be put. Either you're going to create a new buffer or you can use an existing buffer.
Go through
all the buffers and see what? Go through each buffer.
Like you have to travel each element of each buffer and see which is the successor. Then you can put the...
No, if you're the successor, you're fine. You can just check if your timestamp is greater than or less than, strictly greater than or less than. Basically, if it is not concurrent with that message. Just go and look at the message at the head of the buffer, see if this particular message is concurrent with it or not, which means it's either less than or greater than. If it is not concurrent, find the position in the buffer now where you put it. Right? Otherwise, you're concurrent with all the messages in all the buffers. That means you're along a new path, create a new buffer. right? Otherwise, create a new buffer. And insert message at the appropriate position in this new buffer, which is either a new buffer or an old buffer. Okay. And process buffer as before, but now use a different successor function. And the successor function is the one we just saw in the previous slide. Okay, so we, I think, now have an algorithm rather than an outline. Okay. And how did your algorithm work? You didn't do this. You were being a little lazier.
Yeah, I only use one buffer.
You use only one buffer. So if you use only one buffer, how do you go and put two messages that are not comparable in an order there? Yeah, so you can't order the messages, right?
Yeah.
So it's not a buffer, it's a set.
Yeah, in a set.
Right?
So I check all the messages stored in the set.
You check all the messages in the set. Okay, so basically this takes into account that a message on a different path from an ancestor of the current timestamp node arrived, okay? Which we saw earlier. So a dagger message path exists. Create a single buffer for all messages. When a message arrives, put it in the buffer at some position. Okay, positions don't matter. Process buffer as before, except use a different successor function. Search the entire buffer rather than look at the head of the buffer. Okay. So each time when a message arrives, you put it in the buffer, find some message that's a successor of the current timestamp. If so, remove it. Look at the buffer all over again. Find a successor. If so, use it. And if you find no successor, stop. Is it really so bad?
That is okay, since if you want to make many buffers, then you still need to spend some time to decide which message to put in several buffers.
Okay. So in the first case, you're looking at time versus space. Space, both are same.
Oh, yes.
Right? In one case, you have the buffer distributed and replicated. Partitioned. You can have a distributed hash table, right? And in the other case, you have a single buffer. And you're saying if the number of messages is that if you have, in one case you have to sort, and here you have to just look at the buffer again and again, right? And you guys who've done data structures recently, do you guys know of any, the sorting cost versus searching cost kind of thing? When is it, if you have many insertions and few lookups, then obviously your algorithm is good, right? And when I studied compilers, my instructor told me that if the number of items is less than 28 with usual workloads, it's better not to sort, just do a search. I use that as a principle for never organizing things in my house. Okay, I'll just search for everything. I'll never stack anything in my office. I'll just search everything. It's less than 28. Okay, and hopefully these buffers are not very long. Okay, the delays are small and it's all getting through. So I don't think this is a bad idea, but I feel much better with the other algorithm because I know what the paths are. I can order things, I can search things, I can say what's pending along each path. And in terms of, you did it really because you were lazy about coding, right? So I would encourage that. Okay, so hopefully this works. Any questions? I'm more likely to find the time. Okay, so this is sort of the next thing after causality. Okay? And we said, can we come up with an algorithm that immediately delivers concurrent messages while keeping the causality relationships in each path along the tree of messages, right? Assume this algorithm works correctly, and if enough of you implement it and enough of you go and try it out in different cases and it all works, we kind of have more confidence in it, okay? The question is that enough? Okay? Or are we going to still have problems, even if we do this algorithm as we intended to do? Okay? And an example, we've got our causal timestamps, and so far there's only one path, and I've spelled, I want to go for lunch, so I said LNCH, and I didn't say it, together we said it somehow both two users. Let's just take two users for now, okay? Because we're not dealing with peer-to-peer and causality now. Now we're dealing with concurrency, okay? So concurrency issues can be exhibited with just two users. And this is the state of the buffer, of the common state. This is the common state. And the left user goes and decides that this abbreviation is not enough. They also like to type long words. So this user goes and types U. And this user goes and says, oh, put a question mark there. I guess you want to know whether we're going for lunch or not. Okay? So I2U means that at position 2, an insertion occurred. That's what I means. And the inserted character component is U. Okay? So at position 2, I put U, which means anything at position 2 gets moved to after this position 2. Okay? At position 5, a new value got put. Okay, so a new position 5 got created, and at that position, a question mark was added. Okay, and my timestamp becomes 50 at this time because I am the left user, and this guy's timestamp becomes 41 because we assume that the left user had typed LNCH. Okay, and the right user got all 4 characters and decided to go and put a question mark, and their timestamp is 1. Okay, so we're using vector timestamps with just 2 users, and we can detect concurrent actions. Okay, and given that we can detect concurrent actions, we can replay them while honoring all the causality constraints along each path. Okay, what's going to happen when these actions reach each other and we play them? So when this question mark arrives here, where will it be inserted? Before H. And when this U arrives here, it will be inserted? Okay, so when this question mark arrives, it's inserted at H, at this position, and H goes after it. Okay, and in this case, the U arrives here, gets inserted. So we have this situation. Okay. And the problem, of course, is that our operations didn't commute. Right? And so this, we have separate orders. Each the order of message processing here is different from the order of messages processing here. Plus, these actions don't commute. So, the assumption I made when I kept saying that, look, this concurrency won't cause a problem, I kept assuming that operations commute. Like I said, one person resizes the line and the other person colors it. So, we get the resized colored line. Okay. So the whole point here is that causal broadcast is not enough of a guarantee in distributed computing. Okay. And what other kind of broadcast might you have that you might have heard of, some of you? So causal broadcast imposes a certain ordering among messages, right? Can you imagine a stricter ordering than causal ordering? So the ordering in causal is that a cause will be processed before the messages that depend on it. What's a even stronger kind of ordering?
Not only the cause, but all other events happen before.
So you're saying we're not honoring only causality. We're using some kind of ordering besides causality to do what finally? So if I say, every site doesn't have the same order of message processing, right? Only the causal messages are processed in the same order. So a stronger ordering is all messages are processed at all sites in the same order, and that's called atomic broadcast. Okay, so if you go and Google for broadcast, you'll see causal broadcast and atomic broadcast. Those are the two kinds of broadcast. Okay, so in causal broadcast, you're using the less than and equal relationships, and that's fine. Whenever you come up with a concurrent relationship, you can throw an exception, you can process it immediately, you can do something, something that the causality doesn't actually address. Okay? And so it has to do with causality. Causal timestamps allow computer to determine concurrent actions, but they don't tell you how to process them. They do not impose a common or total order which inherently doesn't exist. That's what you were saying. Maybe you use some time or something else as an order, and total order are often important. So if I was to tell you, use the library that I've given you to create a common order in all sites, to make sure that all sites process messages in the same order, could you do it? Is there some simple algorithm you guys could use?
If we could have a relayer.
If you have a relayer, sure, we have a relayer, right? So we go away from P2P, okay, which is what causality was going, and we say, so broadcast supporting total order called atomic broadcast. So far we were talking of asynchronous communication, okay? Asynchronous broadcast, which we haven't quite defined earlier. We've talked about asynchronous pair communication, but not broadcast, okay? So the idea is that you perform some operation O at the site, then two others send the operation using peer-to-peer communication, okay? So, and then they perform received operation, perhaps in causal order, okay? But you did your operation before synchronizing with other guys. There is no synchronization of your action with respect to other people's actions, okay? This is asynchronous broadcast, and there's a theorem that says that you cannot have asynchronous atomic broadcast, okay? We can try to create all kinds of orders, but we never really know. We can use site number and so forth, but you'll get into trouble, okay? And that's why theorems are good and proofs are good, okay? By the way, Jim Anderson does teach a course on distributed computing, which many of these algorithms are proved correct, but with fault tolerance as the application. Okay, I talked to him the other day and I said, what about this and this? And he said, no, we're just looking at fault tolerance. Or not just, we're looking at that different domain, okay? But if you want to study this in more depth, having done the implementation, you'll have a very concrete idea of what's going on there, and then you can do the proofs. Okay? So no coordination performed before performing operation, and atomic asynchronous application unaware. That a broadcast that doesn't take into account semantics of the message, okay, which we haven't in our causal thing. So how can you have synchronous and coordination? As Nick suggested, just use a relayer. And how would we use a relayer now? Before we was performing operation, then saying two others send the operation. Now what would you do? And two others send directly. We want now a common order. We can do this two others through the relayer, but does that solve our problem? That's just like putting vector timestamps on peer-to-peer communication. So how exactly will we use the relayer here? Get state from it. Do not perform operation immediately. And rather than doing two others, you would do now what? You've done the concurrency control implementation. To all. Okay? Perform operation O. To all send the operation using relayed communication. If you do to all with non-relayed, it's immediately executed. If you're using relayed, then to all waits for the message to come back from the relayer. Okay? So when the message comes back, in your receive handler, you perform the operation. In fact, this is the model people use when they talk of causality. They talk about only receives changing the timestamp, not sends. And they assume that each site sends a message to itself also. Okay? Whereas that doesn't quite follow the implementation that we have in our assignment. Because we are taking an existing single user application, extending it, and so we just do whatever the single user did, which is do the operation immediately, and we don't assume that the operation occurs in a filter, in a receive handler. Okay, but that's what you could do, and you perform operation on its receipt. Okay, so we could do this. Would it solve all our problems of concurrency? So what are some of the issues with this approach? The obvious issue is an interactive system, delay, right? Any other issue of semantics?
We now have a single point of failure for our application.
Okay, so we have a common relayer here, and that can be a single point of failure. You can do fault tolerance here, by the way. So when I teach distributed computing, we actually do fault tolerant relayers. That if one relayer goes down, another relayer can take over. I told you guys of the tandem computing computer that Jim Gray worked on. Jim Gray is the guy who did hierarchical locking, and that was the philosophy they used. By the way, Jim Gray is also a Turing Award winner, and the whole idea of logical timestamps was created by Lamport, and he's also a Turing Award winner. Okay, so you're seeing in this class, some of the research that caused the Turing Awards to be given. Okay, from the nested transactions, that was Barbara Liskov stuff, that was Turing Award, and your general knowledge is increased this way also. So assuming that the relay will not go down, we have latency issues. Could something bad happen in terms of semantics? So what's happening here? That when there are concurrent messages, each side gets the messages in the same order, right? That's what we're guaranteeing. Yeah.
So maybe the client one sends the message before the client to us, but afterwards he will see the other message before the message is sent.
Okay. It is possible that client 1 send the message at time 10 o'clock, and client 2 send the message at time 10:05. But the message sent at 10:05 arrives at client 1 first than the message sent at 10 o'clock, right? And this happens at all sites. But they were concurrently sent. There was no order among them. So is that really so bad? We're going to spend maybe 2 or 3 weeks handling the issue that arises here. So client 1 send an operation, and at 10 o'clock, assuming the buffer was at a certain state. And when client 1's operation gets executed, is the buffer in the same state as when the operation was issued? The 10:05 operation got executed before client 1's operation, right? So client 1's operation was sent with respect to a different state than the operation that actually got executed. So when it's executed, the state is not the same as when it was issued. Okay? So each side performs the operation in the same sequence, assuming ordered Unicast. There's a delay because of extra hop. And state of operation issue not same as state of execution, though all sites are consistent. They're all the same, but they all could be screwed up a little bit. Okay. I thought I'd put a little parenthesis here, so I'm a little afraid that what we see here is not my current latest. Let's look at the situation. Let's assume this is the order in which the operations get executed in each site. So what's going to happen? U is going to be inserted at position 2, and question mark is going to be inserted at before H. Right? 2 gets inserted after L. So now H is at position 5. Question marks arrives here. So it gets inserted before H. So this is what happens when the first operation gets executed. This is what happens when the next operation gets executed. Okay? Consistent, but not quite what the users intended. Okay? Common state, but intention violation. Context operation not the same as when it was issued. Right? And can things be worse than this? At least they have the same state. The fact that the context of operation is not the same as when it was issued, can that cause even more extreme problems?
Yeah.
Like what? Can you have exceptions?
They want to delete the same object or
They want to delete the same object. Very good.
Or act on an object that's been deleted.
Or act on an object that's been deleted. Okay. So worse outcome than intention violation. There's only one character, just L. So the first guy decides to delete it, so they can insert a capital L maybe, and the second guy decides to modify it. Okay. So they could both delete it but change it to L. Let's assume this is the order in which operations get executed. So there's no buffer. When you go to modify, right? They both see the same exception. Okay? But that's not what you want. Common behavior, but exception. Okay? So context operation not the same as when it was issued. So let's go and handle the situation next time and see, why we have to spend a couple of more weeks trying to handle this problem. So this is where we left off last time. Assuming concurrency works, okay, the question is, are there still further problems? And we took the example of editing, that we started with a text buffer that was shared among two sites. It was populated by site 1, which put 4 insertions into the buffer. Okay? And site 2 has done nothing so far, just observe them. We have vector timestamps. There are only 2 sites here. We're going to, for a long time, assume only 2 sites. Okay? We'll go to n sites very late. And for 2 sites, causality is not an issue. There are only 2 sites. There are messages arriving in order. We assume we're using TCP/IP. So the only reason I have timestamps is to discover concurrency, okay, conflicts. And we're going to use some algorithm to fix that. And we can use the algorithm we just saw earlier. So now what happens is that site 1 goes and fixes that to LUNCH, and concurrently site 2 goes and puts a question mark here. So site 1 has issued 5 operations, site 2 has issued 1 operation. This timestamp is concurrent with this timestamp, so we know there's something wrong, and we can use some algorithm to make sure. Well, actually, we just know there's something wrong, and we can just process the operation as it arrives. Okay, we know there's a conflict, and if we just process the operation as it arrives, which is what we've done in a causality algorithm. When we go to end sites, we can assume something similar, and we've ended up with divergence. Okay, because the U got put at the second position here and second position here, but the question mark got put at position 5 here, and it moved to position 6 because the U arrived here. Okay, so we ended up with this divergent state, and we said, oh, that's because we have causal broadcast and not an atomic broadcast. In an atomic broadcast, every site will go and process operations in the same order. Okay, so we need the distributed computing guys will say that is what went wrong, that you had concurrency and you try to fix this. The reason why it's not so easy to find algorithms for concurrency that involve causal vector timestamps is because that's just considered something that shouldn't happen when you're just looking at causality. Okay? The concurrency shouldn't happen, but concurrency does happen, and we can say that we can look at a broadcast that's designed for it, and such a broadcast we saw can't occur with asynchronous operation execution. So we did synchronous execution, which and here's a simple way to do it: that operation PC1 goes and inserts U at position 2, but that operation is not processed immediately. It goes through the relayer. Relayer goes and sends message back to the originating site and everybody else through a to-all kind of call. And now everybody sees the same sees lunch, right? It's that point that the operation occurs. And we tried this out, and we said, look, there's a couple of things wrong with it. Firstly, there's a delay. There's an extra hop through the relayer. And secondly, the operation here may get executed with a state of the buffer that was different from the state at when the operation was issued. Okay? So between the time that this particular operation is sent and processed, some other operation might have arrived at this particular site, which means the state is different. Okay? And we saw the problem here, that let's say that the operations arrive in this order at both sites. It's atomic broadcast. So and in that case, we get these semantics. The question mark gets put at 5 rather than at 6, because when it's issued, there's now a U in the buffer, which didn't exist when it was. So when it's executed, there's a U in the buffer, and when it was issued, there was no U in the buffer. Okay, so the question mark got put at the wrong position, and maybe that's not so bad, but maybe it is bad. Okay, certainly the users have to do some extra work, but they all see that it's the same state. Okay, so at least nothing bad happened, no exceptions occurred, but the state is not same, and one of our goals is convergence. Convergence, which is achieved, but another goal would be, and this is kind of hard to define, user intention. The user did not intend this to happen, and it's happened, and we'll try to explain, this lack of this problem in a more formal way. And then we saw that it's even worse in this situation, where the buffer has only one element, and one user deletes the element, wants to convert small l to capital L, so they just go and delete L and small l, and they're going to put capital L later. And the other user modifies small l to capital L. Okay? And what was the problem here? If this is the order in which the operations occur, then the element will be deleted, and then the modify operation will be applied to an element that doesn't even exist. Okay? Look at exceptions. Okay? The context of operation not the same as when it was issued. And this occurred, this is where we left off. This occurred because there was concurrency. Can you guys imagine a single user case where you might want to execute an operation in a context that is wrong? In single user case, when is it important to consider the context of an operation? So when you go from typewriters to word processors, what's the biggest advantage you have with word processors?
We can move text around, copy, paste, insert.
You can move text around, copy, paste, insert, and anything else? Supposing all of these facilities weren't present, and you make a lot of errors like I do. Undo. It's one of my favorite operations. My first PhD student did a thesis on collaborative undo. Okay. Actually, he didn't finish it. I came here. He went to Intel, started winning Best Employee Awards in Intel. All he had to do was write it down, finished it. We published a paper, though. And but he was my first student for sure. So can you guys see the situation here? When you undo, you've done 10 operations. When you undo, which operation will you do? Undo? Could you undo the 9th operation or the 8th operation? Would you have you wanted to undo the non-last operation ever?
Yeah.
You have. It had made sense. Yet your tool will not give you what's called selective undo. And why not? Why not undo the ith operation? Why always undo the nth operation?
The later operation is based on the operation.
The later operations are based on the previous operation. So the context may not be the same as it was when it was done. For the last operation, the context is the same as when it was issued. If you undo that, now the last operation has the same state as when it was issued. Okay? So if I do modify and then I do delete, and I want to now go and undo modify, what will modify do? It says replace at index 1 the capital L with small l and array index out of bounds exception. Okay, so by the way, undo and what we're going to study are very related. I'm not just putting this as for general knowledge. Okay, I kind of do that, but they are related very much. Okay, so undoing non-last operation is done in a context different from when it was executed, and that is why selective undo is very tricky. It can be done, but it involves much more work, and it involves work of the kind that we're going to study in this section. Okay. So now let's go and see what happened here. Okay, this guy put the question mark after H, and the question mark got inserted here. Something wrong happened. Can concurrency control and what we studied in concurrency control explain what happened here? Why we get what we deserve? Oh, we deserve what we get. All this stuff I taught you about transactions. Can the database guys say that you deserve this because you didn't have any transactions here, right? No transaction, no concurrency control. Were there transactions here? Well, there was concurrency. There must have been transactions.
Yes.
What kind of transactions did we have?
You type in the message and you see the message. It should be the kind of transaction.
So you typed, two people acted concurrently, right? That's a transaction. What operations occurred? When this guy put a question mark here, when this guy put a U here, what operations did the person issue? Read and write. What operation did this person issue? Read and write. Two operations. Did they happen concurrently? And was it optimistic or pessimistic transactions? Was it incremental sharing or not non-incremental sharing? Optimistic, guys, remember?
Optimistic.
Sorry? Optimistic. You're both executing on your own local copy from quote unquote some database. Right? And for optimistic transactions, we have to go through a validation state. Did we go through a validation state? No. We just said, whatever happens, happens. And the database guys can say, you deserve this, right? So what really happened was, you guys two operations executed optimistically and did these operations. Okay, who knows in what order they occurred? But, there's a validation that should have gone on and one of them should have been validated. And we basically validated both. And, so both should have been validated and one should have been aborted, the other should have written. If we went through concurrency control and transactions, we would get one of the characters and not both. Okay? If we went through optimistic, which is what we're doing. If we go through pessimistic, what would we do instead? Oh, no, pessimistic is what? No, pessimistic, there's no aborts. Locking. We get a lock, we insert, we release the lock, and so forth. And then the question becomes, are you locking, unlocking at each character? I mean, what are your unlock principles here? Are you doing tickle locks? So we can imagine doing that, but that's going to be more cumbersome, right? And it's going to be more inefficient because you're checking locks often. You're asking for locks often. Okay, so so optimistic, we don't. So should we use optimistic? By the way, if we could, should we use our optimistic here about one of the users? No? Why not?
Because the user has an intent to make a change and it's just saying no.
No, you repeat the work.
Yeah.
Now you want to redo. Redo of something that was not even done actually, right? So with interactive transactions, we don't want lost work. I mean, we might have been disconnected for a while. A lot of stuff will have to get deleted. And there is a fix. We know what the right answer here is. We just don't know how to get to it. We don't want to use locking. Could we just say that? And a lot of people in CSCW, when they look at all the stuff that I'm going to talk about, they get the head pains, and they say, this is a stupid scenario. Why would anybody ever insert in the same buffer at the same time? How about that philosophy? 90% of the CSCW people will. There's just a small group that's working on this, and the other people just say this is a silly problem. Is it a silly problem? No? Can you imagine using it? Have you used it? You guys are post-Google Docs. Okay, this is before Google Docs. After Google Docs came around, all the operation transformation people said, finally we're vindicated. Because they've been really bashed around before that. They go to conferences, they start writing notations, and everybody goes to sleep because it's a formal paper, and finally there was vindication for this stuff. Okay.
But even in Google Docs, I don't think people try to write on the same line all the time.
But it's the same text buffer.
Yeah, it is.
So you want to break things by lines and have maybe a lock for each line?
I think that's what, generally humans just...
Okay, but when I insert a line, how are we going to resolve those insertions? You can't get rid of this problem. Okay, maybe when you're inserting lines, you have to ask for a lock. That is a plausible thing. Okay, but that's still not very fluent. Google Docs uses the algorithm you'll implement is the one Google Docs uses. Okay, and I've had students in class before I found that PowerPoint can record, or before PowerPoint, I've been looking for it for 8 years, and before I finally found the feature, I used to use Live Meeting, a system from Microsoft that they gave it to me for free because I'd spent some time there. And Live Meeting is a collaborative tool, but one of the things is that it allows you to record things, record what you present. So I would have Live Meeting running, and all my students in 401 would go and have Live Meeting running on their computers. And literally, as I was writing my program, this is, I think, 110 actually, when I would actually program in class. Students were correcting my code as I was typing them. So even on the same line, it's possible. And when I saw that happen, I said, let me freeze this video. Let me go replay this video for all the people who are naysayers about OT and show that why people do edit the same line too. Okay, so we can't use locking. We don't want to use optimistic. We don't want to use locking. We don't want to ban this kind of editing. So what choice do we have left? That we've studied earlier. This situation is very similar to what you do in Git, right? I edit, you edit, we have to do merging. And we're going to do real-time merging, okay? Distributed merging. So that's exactly what we're going to do. So this is a non-serializable transaction, by the way, okay? And we're trying to go and merging is very tricky. It's messy. We don't even know what the right answer is, okay? So now we get into trouble. But we'll accept that, okay? And we'll try to come up with some algorithms that make sense. Okay, so if we employed optimistic CC, we would abort, but no CC was employed, hence divergent state. And what are our choices? We can use pessimistic, optimistic, or we can do merging. Pessimistic and optimistic give you serializability. Merging does not give you serializability. It never takes into account what a person read. It's based on what you did, only the writes. Read is never looked at. Okay, and the reason we don't want locking is per operation checking and communication overhead. The reason we don't want late validation is inconsistency, the lost work. Okay, I don't know why I said inconsistency possible. Basically, there is lost work. When there is inconsistency, okay, in optimistic, inconsistency is possible. And when that happens, there's lost work. That's what I'm trying to say. So when we're going to do merging, and I gave an example of merging that if I insert at position 1A and position 2B, then I will insert A at 1 and 3, B at 3 maybe, okay, to take that into account. So we're going to ignore the reason this is application specific. So we're going to look at a specific form of merging, okay? And what we really want to do is transform this 5 into a 6, right, when it arrives. Then everything will be fine. In this case, that's what we want. So our task now is to generalize this particular example, okay, as much as we can. And so I said it's application specific. How specific to a particular application is it? Is it bound to a text buffer, or can this apply to, can this problem be more, is the problem more general? The solution that I just showed you, that you transform the index. Papers have tended to focus on text buffer, and it can apply to
Stream of actions.
any list.
Yeah.
Right? So in your project, you could apply it both to the message history and the text buffer. So I think what I'll do is when I write the project, I'll make it regular credit to just do it for the one of these two. And for extra credit, do both. Okay? The algorithm you write should be dependent on some list type rather than on list of some element type rather than list of characters. Okay? And in fact, the way you modeled your stuff, I think it's list of element, right, in both cases. So that should work out well. Okay? And in fact, this idea of transforming the operation is basically merging. It can apply to other data types also. It can apply to a hierarchical structure. People have done research in that. It can apply to a spreadsheet. Okay, 2 spreadsheets being modified at the same time. So this idea of transforming operations, which is really merging, is more general. Okay? So we're going to assume an index sequence data type for this particular algorithm that I'm going to talk about. So some arbitrary element type. And this is not the way people talk about in operation transformation. They talk about text buffer, essentially. But we'll do this. And it could be a string, or it could be a character, okay, in your project. Okay? And we're going to assume there's insert and delete operations. And in fact, in my slides and in your project, you can just assume only inserts. Okay? Once you've handled inserts, handling insert, delete combinations, delete combinations is work, but the amount you gain from doing that is small compared to just doing insert. Okay? So in my implementation, I think I did do delete. I forget. Okay? In your demos, you might have seen only inserts because I think I addressed only that part. Okay? But for extra credit, again, feel free to go and do deletes and all combinations. Okay? And it's not going to be hard. It's just tedious. Okay? Okay. So let's see how things are going to change from our causality algorithm. Okay? In the causality algorithm, we had timestamps. Okay? Do we still need timestamps in an operation transformation algorithm? Involving only 2, we're going to have only 2 sites. Okay? If there was no, so the P2P communication and causality doesn't really arise. There's only 2 sites. I'm going to receive from that site messages in order because I'm using TCP/IP. So do I still need timestamps? And I hinted I do. So why do I need timestamps? We're going to transform operations. And for transforming an operation, do I need to know the timestamps of the operation? Do I need to know about timestamps at all? If an operation arrives from the other side, after it has seen my operation, will I ever transform? The transformation occurred only because there was concurrency, because the context of the other operation was not the same as my context right now. So to transform or not depends on, so I need timestamps. Okay. Do I need a received buffer? Why not?
Just transform it immediately and receive the
Okay, because it's not as if the other site's message is, as if I'll receive a message before its cause, right? The message either was generated by me or by the other site. The other site's messages will arrive in order. So it's not as if I have to buffer the other site's messages, because I'm assuming only two sites. If I had n sites, yes, I need a receive buffer. Okay, and we'll see we won't even quite go there. Okay, and Google Docs doesn't quite go there.
But we are assuming that it is coming in order, right?
From the other side. We're assuming it's coming in order, so we don't need a receive buffer. So do I need a buffer at all? I transform 5 to 6. Why? Yes, I transformed 5 to 6 because my timestamp of the timestamp of the message is oh, this should have been 50, 40 and 41. 50 and 41, right? Yeah, sorry. I transformed it because 41 is concurrent with 50. I needed the timestamp. That's one reason why I transformed. Did this particular operation get transformed? I2U, this 2 went as 2. This 5 became 6. Why was this transformed and not this?
Because the action of the question mark was already done at the end. And PC2 already has the question mark.
No. Both operations were executed concurrently. Okay. This guy is LNCH. I seem to have removed some things here. Okay. This is LNCH. This is LNCH. Then this became lunch, and this became lunch with question mark. Okay. In both operations were executed concurrently. How come and why did I increment the index? Why didn't I decrement the index? I mean, we know that this should become 6. Okay. And if that becomes 6, then we'll have the question mark at the end. The question mark is at the end here. I inserted U at position 2. So what was my criteria?
Index 2 is less than, yeah, basically index 2 is less than 5 is what I understand. Because you inserted before, how do I put it?
Yeah.
Because insert operations do not affect the indexes before that.
Yeah.
Okay, so insert operations don't affect indices before them. Right? Okay, that's the way you want to look at it. So what happened here? This particular thing was done at 5. Okay, and it was made 6 because something before it came that was concurrent with this. This guy did not get transformed into 3 because something that was done concurrently with it had an index greater than this. And that did not affect So I had to compare this timestamp and this index with what? I had to compare this timestamp with this timestamp, or what correct timestamp, and I had to compare this index with this index. The index of this is a remote operation. This is an index of and where is that operation? It was issued. So my question to you was, do I need a buffer? And the question is? And it was originally a receive buffer, and now it will be a local buffer, send buffer, if you will. Okay? So we've got the basic idea right now. Okay? Assume message arrived in order from other side. No need for received buffer. Okay? Still need timestamp to discover concurrency. And the question now is, what is the general rule for transforming an operation? And now, now we are seeing here. So this is the picture I really should have had, right, before to discuss things properly. So we transform 5 to 6 because a local operation, increment index of remote operation, if it has higher index, then assume for now only one local operation was executed concurrently. Okay, it's just a headache to consider more than one. Okay, we'll take that headache later. Okay, so the index of remote operation was more than the index of the local concurrent operation, so we transformed it. So remote operation R is transformed. Not every remote operation is transformed. Only concurrent remote operations are transformed, and only if the indices are greater than the indices of local operations when we are considering insert. Okay, a lot of qualifications here. Okay, so based on index of concurrent local operation L, so we issue an operation RT, which is different from the operation R that was received, which is transform. So how would you read this?
Remote.
So transform, the value is return value R, that is R transformed with respect to L. L is not transformed. R is transformed, and we get a new, I'm using functional here. Okay, so I'm saying I get a new value back. I don't change the R originally. Okay, let's just be safe there. And we apply RT instead of R at local site. Okay? So now we need two things. We need an algorithm to do all this stuff, to call transform, the main algorithm, if you will, and we want the transform function. Okay? And one of them is called the control algorithm. The other is just a transform function. We can have many transform functions. Okay? The transform function can return R back, saying, you know what, I don't need to change anything. The operation that was received is exactly the one I'll issue. Okay, so I'll just return that value. And we'll say that R has been really transformed if RT is not equal to R. We'll call the transform function, but the transform function may not really transform the function. Okay, and we need local buffer to store L rather than, and we don't need a remote buffer. Yeah.
Why do you only transform the remote operation and not the local operation? Because it's possible, because if you look at from PC2's point of view, it will receive a insert at position 2, and its local operation will be insert at position 5. So in that case, you should transform the local operation.
So you're saying we should transform the local operation also. In this example, does it make sense?
Yes.
It does? Okay. By the way, what you're saying is very profound. Okay. And that is a result that there have been many papers, and one of those papers exactly found that problem. But I don't see a problem here. Okay, that's a good sort of top-down thinking to do. Let's do some bottom-up thinking. So I had to come here. I came here. I transformed this operation to this. And what you're saying is that what? I mean, this local operation already got executed. So why do I transform it? It's in the buffer. So why do I have to transform it? The remote operation has not been executed.
When you do an undo later.
So we are not doing undo right now. That's another headache.
So our operations are being at PC2.
PC2, it executed question mark. It put question mark in here,
At position 5. Or
position 5. And then you came and got inserted before.
Okay.
Okay, so it's the remote guys that are coming. And you know, when you start doing undo, that's a totally different thing. And you can just imagine there's many kinds of undos. You know, do you keep the undo history same or not same? If you keep one undo history for everybody, then sure, the remote operations go in the history, the local operations go into the history, and then you just employ regular and undo, no problem. Okay, not quite, but still. It's when you have local undo, which is what my student did, then you have to do selective undo. Because you might want to undo your last operation, which may not be the last operation in the sequence, and that becomes trickier. Okay? Okay, so everybody understand this so far? So here's my control algorithm, my main method, if you will. Okay? Given remote operation R, concurrent with exactly one local operation L, let's assume that, RT equals transform RL, execute RT, and site dot timestamp increment R dot site. Right? That's my algorithm now. Right? And this transform function magically has to work. If it works, I'm just writing this modularly. And this part is called the control algorithm. There's many things that are wrong with this, by the way. Okay? But this is exactly, I'm telling you the history as it occurred, as I've seen it in front of my eyes, in fact. Because I've read these papers and I've read this successive papers and so forth. Okay? Questions? And so there are two components in an OT system. Transformation function, which handles single local and concurrent operations, and it can take various combinations. It can only consider insert, delete, whatever. Okay, and control algorithm, which is independent of what operations are being considered. Okay, it says some magic transform function occurs. Hopefully, it's correct, and we've got to figure out a correctness criteria. And it just goes and updates it. It processes the buffer. It goes and adjusts the local timestamp. Okay, and it calls transform function. Okay, both must be correct, and both have not been correct. Okay, and they're tied to each other. Sometimes people change. When things go wrong, they change the control algorithm sometimes. They change the transformation function sometimes. Okay, and there's just been a lot of papers in this area. Okay, only some of which are correct. Okay, and I'm guilty of being the editor of papers that were accepted that were not correct. Okay, because what do? You just give it to reviewers, and they do their best job too. So, in fact, to be very honest, I got so tired of this that I just resigned as an editor afterwards. I said, I can't handle this, and let somebody handle it. Because I haven't done research in this area. I've done indirectly. So somebody who I really trust from Europe, she became the editor, and I recommended her, and that's good. It's a headache now. Okay. So let's look at the transform function. Okay. Transform function takes two operations as arguments, okay, and returns back an operation. Okay, and you can imagine this transform function being broken up into multiple cases. You can consider it to be an overloaded function, or you can consider some a function that dispatches to other functions. Okay, so you can say if R dot type is insert and L dot type is insert, then return transform insert insert, or return transform insert delete. Transform, delete, delete. And I've done it this way just to make things more clear to you. In a nice language, I would have them overloaded with different types, and it automatically selected. Okay.
So the local operation could be many local operations.
We're going to assume only the transform function will take only one local operation and one remote operation at a time. The control algorithm is responsible for handling multiple cases. And I've just made some assumptions right now and said, one operation. Let's just, this is going to be a long story. Let's not tell you all the details at one time. Okay? Let's just get it incrementally. Okay? So you guys know of the deductive and inductive way of teaching? Anybody heard these terms? So do you find my style in some ways different from the style, not my accent, not my slides, different in some major way from styles you might have seen elsewhere? Why was I so bothered when you guys weren't answering questions? And also, so deductive is you present everything at one time, properly. You don't give half pieces here and say, okay, you don't come up with examples first and then with algorithms. Deductive is you come up with the algorithm, then you come up with the binary search, then show this case, this case, this case, this case, and you're following everything. Okay? You don't need, I mean, it's very hard to come up with the algorithm on your own. You don't ask questions really. You just present things and say, did you understand? Okay? And some very clear speakers do exactly that. Inductive is you let it be derived in class. Okay, so my first course I would talk to operating systems. So I started off by saying, what's an operating system? Okay, definition, and we spend half an hour on that. Okay, what components should it have? Okay, let's talk of concurrency. Okay, or scheduling. What can you have? And so it was all like a story that got created from class. And I used to give full-fledged class notes, and it was interesting that after the nth time I taught it, everybody thought they had very individualistic discussion in class, but what I had in class notes was exactly what they had said in class. Okay, maybe I was orchestrating things a little bit. So ultimately, deductive and inductive are not different in the textbooks you write. And which would you guys prefer, inductive or deductive? I mean, I know I'm using inductive, so you can say that just to please me. You can say that, but what are the pros and cons? See, I'm being inductive here.
I think the inductive, you will have more interaction between you and students.
Yeah, you have interaction. And what about when you take the exam, which is going to be, which scheme would have been easier? Deductive? Would you remember everything? Inductive, you had to come up with it yourself. That's that. So
there will be some misunderstanding.
There can be some misunderstandings. So it's a pro and con. That's why there are two styles. There's not one that wins over the other. And I've taught writing classes also. So this is where we talk about that in depth. And teaching classes, presentation classes. And that's exactly it. So, but tier 1 universities, the top tier universities, the students in those universities learn better with inductive. Tier 2, and just tier 2 in terms of ranking, okay, deductive, they work a bit better. And in terms of research contribution, neutral. A lot of deductive people do very good research, especially in the sciences. And so there's pros and cons here. Okay? So we're going to do very inductive here. Examples, and in the end, we are still not going to be convinced that it works. Okay? But even with deductive, you won't be convinced, as long as you don't have the last paper I accepted in this journal had a proof of correctness also. And then, of course, the next paper I got from there showed the problem with the proof of correctness. And so, it just gets, but there's, there's no proofs mostly in this field. Okay. And here's my transform, insert. Take operation R and L. And we do want to make sure that we are going to use a functional approach. So what we return is not going to change the operation we got. Okay? So we create a deep copy of the operation. If r.index is greater than l.index, rt.index equals r.index plus 1. Right? Can't debate much with this. Okay? This is called an inclusion transformation. What's the goal here? The goal here is that concurrent operations occur, and when everybody is quiescent state, when everybody is settled down and all the messages have reached each other, what should happen? The same state. Right? Now I can achieve that many ways. The moment I see a concurrent operation, I can clear the buffer. And you won't like it. Just like optimistic transactions. But I have achieved the goal of consistency. That I detected a concurrent operation. I know I executed an operation that was concurrent with the other guy's operation. Just clear the buffer, start writing the paragraph again. Right? This is inclusion transformation, which means intuitively the word English. Again, kind of went quickly on this. Oh, you can read this and what does that really mean? I'm returning a new operation R, which is not clear buffer. Okay. How is that related to the original R? If the original R inserted a character, does the new R also insert a character? It does. It just inserts at a different position. So you didn't lose work. You didn't clear all. Okay? So what you did was what you ended up doing was including the effect of L into R. Okay? Because L got issued, the index of R should change. But you didn't exclude the effect, which is something called exclusion transformation, and you didn't just go and erase everything. Okay? And this idea of inclusion transformation is more general than concurrency. When we do undo, similar kind of things happen there also. You include the effect of another operation on an operation. Okay? In this case, the operation, we're including the effect of a local operation on a remote operation. Transformation function is more general. It just includes the effect of one operation into another. It could be both local operations in undo. But in this case, I've called them L and R for local and remote. And we including the effect of L into R. L got inserted at the previous index. So R should now have a higher index. Okay? That's inclusion transformation. Because there are other uses called inclusion transformation. So, okay, now that we understand this, is this correct? And more important, what's the correctness criteria? How can we go and say that formally? And I kind of said that to you, that it should be the case that when all messages at quiescent state, the state should be the same. Okay? And let's do this diagram. As I talked about earlier, we are actually diverging along two different paths, and then at some point convergence also happens, right? Okay. And convergence and timestamps was different, that I just sent a message after I received messages from other sites. Now we want our state to be converging also. Okay. So what happened? At site S1, operation O1 got executed. At site S2, operation O2 got executed, right? Now site S is at state S1. Site 2 is at state S2. We want now to execute an operation at site S2 that brings it to S12, and we want to execute another operation at site S1 that also brings it to site S1. Okay? If we just execute O2 at site S1, we may not arrive at the common state. So we are, rather than executing O2, we are transforming O2 with respect to O1. Okay? And at site S2, we are not executing O1 directly. We are transforming O1 with respect to O2. And the transformation function is correct if S01 T02 O1 is equal to, O1 T02 O1 is equal to O2 T01 O2. Then that function is correct. This is independent, given two operations, O1 and O2. O1 T1 O2 O1 should be the same as O2 T2 O1 O2. Okay, this insight came many years after the algorithms had been proposed. Okay, the first algorithm got proposed in 1988, a guy called Clarence Ellis, and it got published in the Premier Database Conference. Okay, and then it had problems. Okay, and a guy called Matthias Ressel came up with some of these ideas. Okay, and I told you I was the editor. I was also the reviewer of some of the papers. And maybe his papers were wrong, or I wasn't understanding it correctly, but I'm guilty of having rejected some of the earlier papers. I feel very bad about that. But Clarence Ellis was on vacation that time. for various reasons, he was on leave. So I didn't feel comfortable just accepting the paper saying that Skip is wrong. He was, so anyway. But that's sort of a fundamental thing, okay? That there's a proof of correctness for this. Now, T can be inclusion or some other function. If it just does remove all, it's right. We want it to do the right thing also, okay? But this is the minimum we want it to guarantee. We want to also make sure it does the right thing, okay? That the converged state is what we want, but it should at least converge things, okay? So this picture is going to be very important. This is a distributed merge problem. It's not that we're going to a central server and getting a common state back. We are doing a distributed merge where my data goes to you, your data comes to me, and our states just converge. Okay? Okay. What happens in the equals equals case? What if both of us insert at the same position? In this case, neither operation will be transformed, right? If neither operation is transformed, can we get into divergent state? So let's say it's LUNCH. One person puts a question mark, the other person puts an exclamation mark, right? So I say, the question marks goes at position 6 from site 1 to site 2. The exclamation mark goes from site 2 to site 1. So the exclamation mark will go where in here? Before or after question mark? Before. And the question mark here will go before or after exclamation mark? Neither operation is transformed, okay, as this picture shows you. So we have inconsistency. Inductive approach at work here. Now we're going to fix this problem for this example. So how should my algorithm? My transformation function is not right.
You potentially settle on one combination and have them both arrive at the same state.
So that's what we want. We want to settle on one combination. How do we do it? How do I change my algorithm? They're both running this transformation function at two different sites. My function says if it's equal, just let it go.
You can arbitrarily choose one of the values.
Sorry?
You can arbitrarily choose one of the values to be inserted first.
But how arbitrarily? But it has. One side can't choose. Arbitrarily means what?
You can choose like the one with the lower, which occurs first in the alphabetic order.
Okay, so
Something like that.
so you mean you look at the characters, and whichever character is in the ASCII set. We better design ASCII to be such that it does the right thing, huh? Yeah, that's an interesting idea. And what if there are, we aren't going to n sites here. We're going only 2 sites. What if there can be insert delete combinations also. So we need to sort of, you're trying to give priority to one of the operations, and you're giving it based on the value. What if one is a delete operation, one's an insert operation? Then there's what do you compare? So something else we could look at.
Maybe based on the user.
Based on the user.
Like
Okay,
priority or for the users.
or the alphabetically, Alice wins over Bob, or Alice, Alice, Bob, Kathy, right? Guys, that if your name is early in so if your name is early in the alphabet, are you more likely to succeed or less likely to succeed? Why? You get called first. You get to answer questions first. The inductive approach works better for you. Right? So we can let Alice win, or we can always, So in this case, for insert, we could use the lower character. But what we can do, so this constraint is not working. What we can do is, so this is, like I said, and insert concurrent text at same position in order of priority. Okay, somehow give them priority, and we are going to have now ID associated with each operation. Okay, and if r.id is less than l.id, that means r is not as important as l. That means r is the one who moves. L stays put. Okay, and I think in my examples I assume that site 1 is less priority than site 2. Okay, so Alice is less than Bob. Okay. Okay, so now the same. Now we're going to that will, that's more likely to make this win. Okay, this correct. Okay, so you guys, so now you see what happened. I6 remained I6 because it was site 2, which has higher priority. I6 here became I7 because site 1 has lower priority, so that goes there. Okay. Okay. Another question now. Can we assume still there's only one concurrent local operation? Can you imagine 2 concurrent remote operations with respect to a single local operation? And what would the algorithm be in that case? So in this example, let's see what might that mean. I've inserted, say, you. You could have done what concurrently? Inserted question mark and exclamation concurrently. Something concurrently, right? That's possible. So my control algorithm should do what now? Or so what would happen now when the second operation occurs? When the first operation occurred, we transform it with respect to this particular element. When the second operation comes, what do we do? Do we transform it or do we not transform it? We transform an operation when its context is not the same as when it was issued. So the first operation comes, I don't say we transform it, we call the transform function. And should we call the transform function when the second operation also arrives? Yeah. The context is not the same, right? So given any remote operation R, concurrent with exactly one local operation, we transform the operation. It's not just that once a remote operation arrives, the subsequent remote operations which are concurrent are not transformed. Okay? Here. So this is lunch. This person types U and this person puts question mark and exclamation mark. Okay? So when I5 arrives here, it should become I6. And when I6 arrives here, it should become I7. Right? So I5 becomes I6. I6 becomes 7. Okay? So now the question becomes, how long should I keep this particular element? It's not as if the first time I've been used, I can remove it from the buffer.
After the other timestamp is bigger than
as soon as a timestamp arrives that is bigger than this one, I remove the element from the buffer. Okay. So let's say somebody inserts element 8 here after they've seen U. The timestamp of that is 5.3. That's bigger than this. So no need to transform, okay, because it's not, even though the index is higher, the timestamp is also higher. Okay, we just issued I8 as it was arrived, insert 8, And we know that each subsequent message will have higher timestamp. Remove all locals from buffer with timestamp smaller than timestamp of received message. Okay. Okay. Okay, we'll carry on from here next time. Okay, so let's see where we were last time. Okay. We started with an intuitive idea of transforming operations. Okay. We said, look, if we have two users that execute concurrent operations, one user goes and puts an L here, the other user puts a question mark, puts a U here, and the other user puts a question mark. And when the U is put at position 2, this index is less than the index at which this operation was executed. So this operation can be executed untransformed. Okay? But when the question mark arrives here, it really had to go after the H. Our operations don't say after a particular object. Okay? Our operations say at a particular index. If you could have every character have a unique, every insertion have a unique ID, okay, and your operations were after or before, then things would be very different. Okay? But we're assuming a normal text editor. And any of the previous solution is just going to be very space costly. So when 5 arrives here, the H has moved because of the insertion of U. So when question mark arrives here, the question mark should be done at 6 rather than at 5 to reflect the fact that the H has moved. Okay? So we wanted to transform the operation. That was the intuition. The question was, can we come up with an algorithm to do so? Okay? And it seems like a very simple thing to do, but it's a very complicated thing, as we kind of saw last time, and we're going to see more of that today and on Wednesday. Okay, so we said that, look, there's going to be two things here. One is going to be a transformation function that takes two operations and transforms one operation with respect to the other operation. Okay, this is an inclusion transformation that we look at. So remote operation arrives. We don't want to execute the remote operation directly on our buffer. We want to see any concurrent operation that executed, concurrent local operation that executed at our site, and transform the remote operation with respect to the local operation. Okay? So given two operations, this function returns a new operation. And then that's just a function that takes two operations as arguments. There's some main algorithm or a control algorithm that calls this function, and it may call that function repeatedly because you may have multiple concurrent local and remote operations. Okay, so this is something that just says, give me two operations, I'll give you a correct result. The control algorithm says, okay, I'll apply the transform functions in a proper way to make it work for multiple local and concurrent operations. Okay, so we separate these two things, and both must be correct. And as the history of this field has shown, that as humans we err, and people have erred in both of these dimensions. Okay, and like I said, I'm going to show you the algorithm inductively. I'm going to take examples like I just saw, generalize that to an algorithm that seems to work for that example and some other examples, then come up with more examples, generalize further, and so forth, okay, till we come to the final algorithm that you have to implement. Okay. We needed both algorithms to be correct, and we wanted some kind of correctness criteria. And for the transformation function, the correctness criteria was described as like this, and I think we saw also a diagram. If we haven't, we'll see it soon. So the idea is that O1 and O2 were executed in the same state, S, at two different sites concurrently. Okay? And O1 got executed first at site S1, and O2 got executed first at site S2. Okay? Both at state S. And what we want to do is, when O2 arrives at site S1, we don't apply O2 directly. We apply some transformation of O2 here with respect to O1. When O1 arrives at this site, we don't apply O1 directly. We apply the transformation. The transformation function can return back the operation O1. Okay? Whatever its first argument can return back. Okay? So we do TO2 O1 here and TO1 O2 here. Okay? We call it the same transformation function. at both sides. Okay, so what we want to happen, we want the transformation function to be such that O1 T O2 O1 is equal to O2 T O1 O2. Okay, and we can devise a transformation function as we wish. We wanted an inclusion transformation where we include the effects of the remote operation and we don't exclude the effect of any operation. Okay, so we could clear the buffer each time we see concurrent and we see concurrent operation. That would make both results be the same, but that's not so good. Okay, so we want to preserve editing. Okay, and we saw one function. We saw one implementation that only looked at the indices of the operations. Okay, and said that look, if the remote operation, the one we are transforming, has an index greater than the operation we are transforming with respect to, then bump up the index. Okay. The question was, what if the indices are the same? And we had one suggestion that look at the ordering of the characters, and that would work. But we did look at a more general scheme where we don't have to look at what the person entered. We look at the IDs of the users and say that some users are more important than others. Okay, and their insertions don't get moved by other people. Okay, so if your priority is less than the local guy's priority, okay, which is decided by IDs, then we move your index. Okay, you're less priority. Otherwise, we don't move your index. Okay, the priority is the same. This function is evaluated the same way at both sides. We're just looking at two sides right now. Okay, and so we'll get a consistent ordering. So this is the transformation function we came up with. Okay, questions so far? Okay. So like I said, we could give priority to characters or to the users, and here we're giving priority to the users. Okay. So our algorithm, our control algorithm, first assumes that there's only one local concurrent operation. Okay, we'll try to generalize to multiple local operations soon. Okay, so it says, given remote operation R concurrent with exactly one local operation L, find the transformation of R with respect to L and execute R, the transformation. Okay, and again, RT could be R. And as in any clock algorithm, virtual clock algorithm, now that we process this operation, we increment in our timestamp the ID for the remote site, the count for the remote site. Okay, so we have to now generalize this algorithm, and even before we generalize the algorithm, the fact that we have to transform a remote operation with respect to a local operation means that we must buffer the local operation. Okay, after we execute it, we buffer it, and then the question becomes, how long do we keep it buffered? And now we worry about the fact that there may be multiple concurrent remote operations with respect to a local operation. Okay, so what happened here was, we went through this last time, so I'm going through this quickly. The question mark and this exclamation mark got executed concurrently with the U. Okay, and because we know that 4-1, 4-2, and this was at 5-1. This was executed at 5-0. This was 4-1, 4-2. So both of these operations had to be transformed with respect to this operation. So our control algorithm is not quite right. Okay, we have to now make that a loop. And when this operation arrives, this user had seen all 5 operations on the local user, and then executed the third operation at this site. So at this point, 5-3 is greater than 5-0, the timestamp here. So this particular item can be now removed from the buffer. Okay. So whenever a remote operation comes in, we compare it with the head of the buffer. If the timestamp is greater than the head of the buffer, we remove the head from the buffer. Then we compare with the next operation, and we keep doing this till we removing items till we come up with a concurrent operation. At which point we apply the transformation function. Okay. So now the question. So in the previous slide, I haven't quite come to the control algorithm right now. Let's. I think I probably gave you the algorithm last time. Okay. That's where we left off. Okay. This is the new stuff. So what's happened here is that these two operations were both executed here concurrently with respect to one local operation. Okay? That's why we had to keep the item in the buffer for a while, not after the first time it's used, till we come up with a future operation that's got a higher timestamp. What's a dual of this situation? Okay, so we have at the local site two remote operations that are transformed with respect to a single local operation. What's a dual of that? Yeah.
A single remote operation being affected by multiple local operations.
Okay, a single remote operation being affected by two local operations. And affected means that we have to go and transform it with respect to both of them. And if it's affected by both of them, then it'll be transformed twice, which means that the transformation result will be different from the input. Okay, so how could we create that situation in this example? That's a dual. What's a dual? A remote operation transformed with respect to multiple local operations. Okay, and how could we change our example?
So PC1 typing 2 type twice, and the PC2 type another message like that. So it needed to move twice.
Okay, so PC1 types two messages, and PC2 types one message. But that's exactly what we had here, right? We had two items from one PC and one item from another PC. So do you want to give some more constraints? In this case, the two items both had indices greater than this guy. In the dual situation, what would happen?
Or less than.
The two operations would be less than, have indices less than the site that executes one operation, right? So that's the key here. So we have use NCH here, okay? And the first user now, well, I got things the other way around now. So just to make things interesting, I guess. Site 2 enters L and U, okay, at index 1 and 2. And site 1 is the one that puts the question mark now, and its index is greater than. Okay. So what's going to happen when this particular operation arrives here? Will it get transformed? Index is less than 4. Won't get transformed. When this operation arrives here, doesn't get transformed. Now, when this question mark arrives here, it's at index 4. Right? Should it get transformed with respect to this particular operation? Become 5. Should we again transform with respect to this operation?
Yeah, 6.
Should become 6, right? So 2 entries got put before it, so it should go up by 2 indices. Okay. So let's go and just see this. This operation arrives here. Operation, the L arrives at site 1. Okay. It's applied. Okay, LNCH. Now U arrives here without transformation. It's applied. Okay, so we have lunch here, and now the question mark arrives here. It's compared with the first concurrent local operation. It's transformed with respect to that. So it becomes now, oh, I made it 6 directly? Okay, so it must have made it 5 before, right? And so what we have is a remote operation transformed with respect to multiple local operations. Okay, so we have to run the transform function with respect to all concurrent operations in the local log. Okay, so to apply, do transform. We have to compose the transform functions. Okay, now you see why the control algorithm is different from the transformation function. Transformation function just says, give me 2 operations, I'll do the right thing. And the control algorithm says, now I'll just call you multiple times, perhaps for a single operation. Okay, because a single remote operation is now being transformed multiple times. Okay. So control algorithm now handles multiple concurrent local operations using transform function. And the transform function itself just addresses a single concurrent remote local operation. So how would we now change this algorithm? Actually, it's a dual situation that requires us to change the algorithm. The original situation, when we had multiple remote operations concurrent with exactly one local operation, that previous algorithm just worked fine. Okay, because for each remote operation, you transform with respect to the one local operation. Now we have multiple local operations on the buffer. So it's easy to go wrong. So let's go and see exactly what we'll do. Okay, so for each remote operation, for each local operation in the buffer, what do we do? Transform this with respect to that operation, and then
Get another
local operation. Give it what?
the previous result.
Previous result. Okay, so we'll have to make R equals transform RL, and give R right back here. Right? And then finally execute this. And we execute the operation only once, and we bump up the timestamp to that one operation that's arrived. Okay? So given remote operation R concurrent with local ops L1 to Ln, for each L, R equals transform RL. Okay? And we are giving to transform the result of a previous transform. Okay? Execute R and write the timestamp. Okay? So from our example, we've come again inductively to the algorithm. Okay? Everybody happy with this? Convinced it works? This was the first algorithm that was published in the literature. I forget whether it had handled, the first algorithm had handled the concurrent insertions at an index, same index or not. Okay, but I told you, I think it was Sigmod. Sigmod is the premier database conference. It was Sigmod 88, I believe. This is one of the most referenced papers in this field, Clarence Ellis. And I think he had a co-author also. Okay. Okay, so in our examples, we've seen that transformations occur at either site 1 or site 2, but never at both sites. Okay, so let's just go and see whether, firstly, how would you, so what's an example of transform, can that ever happen? That transformations occur at both sites? Can we come up with an example here? I mean, in a concurrent phase, not in a sequential phase that, first it occurred here, then the synced, and then it occurred the other site. That there's a set of concurrent operations executed at one site, a set of concurrent operations executed at another site, and both sets are transformed, are changed. I'm using the word transformed in an overloaded fashion. Transformed could mean that I run the transform function, but it may not change anything. Okay, or transform could mean that it also changed. Okay, And from context, it should be clear. So can we have it that one set of operations, concurrent operations, another set of concurrent operations, and some members of one set get transformed, some members of both sets get transformed?
They can do L and question mark on both ends and different orders. In this example.
Okay, so basically what you're saying is what happened so far was that one side either inserted things before or after the indices of the other side. And now what do you want? You want,
Like before and after in different orders.
well, before and after is enough, right?
Yeah.
Because we just want concurrent operations. So we can fix one side and say it did only one operation, just to make our example simple. You'll see the amount of work I've gone through in creating these animations. Okay. Whether it's useful or not, I don't know. So we have one side, let's say, just execute an operation at some index I. Another side execute an operation that is less than I, that is at index less than I, and also an operation that is at an index greater than I. Right? So because it did less than I, the first site's operation will have to get transformed with respect to the second site. And because it did greater than I, its operation will have to get transformed with respect to the first site. Okay? So let's come up with an example here. So all examples so far involve transformations at one site, transformation both sides. So we have UNCH, and this side puts a question mark at position 5. This side puts an L at position 1 and an exclamation mark at position 6. Right? So what's going to happen now? When is this an L? That's what I thought of, So this is probably one of the most confusing things. I. It is IL1. Sorry? Oh, I1L, sorry. Yes, right. So when I1L arrives here, will it get transformed? Okay, so we'll get LUNCH. Okay. When 5 question mark arrives here, will it get transformed? So 5 question mark will get transformed with respect to this guy, and 5 will become 6. Then it has to be compared with this one. When they're both at the same index. So which site? We compared in order of IDs, right? So site 1 has less priority than site 2. So when it's 6, will 6 get moved to 7? It's got less priority. Less priority means you move. Okay? So this 6 will become 7, and it will come after the exclamation mark. Right? I've got animations to, in case this is too abstract, but I just want you to go through the algorithm yourself. Okay, when 6 arrives here, what will happen? Will it get transformed? When the exclamation mark arrives here, what will it get transformed? The local operations at index 5. 5 is smaller than 6. So it will come before or after question mark? After the question mark. And this question mark came before or after the exclamation mark? It became 7 and after. So you have a problem. Okay, let's see whether there's a problem. Maybe all this hand waving wasn't quite doing the algorithm right, so maybe went wrong. So when L arrives, okay, when I1 L arrives, remote operation is not transformed. It becomes this, right? Now when the question mark arrives, it's compared with the first one. Its index is greater than that. Then it's compared with the second one. Its index is the same as that. So it's transformed. And let's put there. When this operation arrives, it's 6 exclamation mark. It becomes 7. Yeah, Nick.
Alright, so the question mark is originally index 5. When it's transmitted, the transmitted message is index 5.
Yes.
So
it first is compared with, our algorithm goes iteratively through the loop, right? So it's first compared with this guy.
And incremented.
Becomes 6.
Right, okay.
Then it becomes 7.
Because now we're looking at comparing the user IDs.
Now we compare the user IDs.
What? I'm sorry?
Yes, we're comparing the user IDs.
Okay.
And the interesting thing is the user IDs were never compared here. That's the funny part. That's a symptom of what the problem is.
Shall we change the local buffer for PC1? When the operation I1L comes from the PC2, the I1L operation doesn't change, but shall we change the I5 question mark from PC1
Okay.
in the buffer?
So what you're saying is the remote operation I1L, its index is less than this guy. So we don't change it. And you're saying what's in the local buffer,
Should change.
Should be changed.
its index is greater than this. So since we have this transform function, let's just use it here also and change it. Why?
The operations afterwards may be dependent on that function.
So what happened here was, yeah, go ahead.
The actual position is changed because after the PC1 received the first message from PC2, so the length become bigger. So I mean, but when he received the later message, the things was not intended to compare things. Yeah.
So what you're saying is that the later operations should consider the fact that this local operations index is essentially now 6. Okay? So why are we transforming? We are transforming operations to include the effect of one operation on the other. Right? So when a remote operation arrives here, we go and include the effect of the local operation on the remote operation. We should similarly, because this remote operation got executed in our buffer, okay, we should include the effect of the remote operation in the local operation to reflect what this operation now is indicating. It used to be at index 5, but now it's effectively at 6 because some operation from the remote side got inserted something before it. So this transform function doesn't always take as the first argument a remote operation and the second argument a local operation. It could be the other way around too. We could transform a local operation with respect to a remote operation also. And that will make it work in this example at least, right? Okay. So we have an inconsistency. Symptom is we never compared user IDs at site 1. What went wrong? effect of this operation, the remote operation, on local operation not recorded. Right? We must change firstly the timestamp. We should also indicate that, look, now our buffer, this operation is not 50, it's now 51. When we include the effect of operation 1 from PC2 in here, we should go and change this timestamp also. And we should change this index, if necessary. So transform gives effect of an operation on another operation. We have used it so far to get effect of local operation on remote operation. We need to also use it to determine effect of remote operation on local operation. Okay? So this is very interesting, okay? That we run transformation in pairs. Here's the operation. It gets put in the local buffer. It also gets sent remotely, right? When it gets sent remotely, we transform it with respect to the local operation here. We also transform it with respect to the remote operation when it arrives here. So the same transformation is computed twice at both sites. Once before applying here, once after it has been applied, to take into account future operations that will come from the other side. Okay? Similarly, this operation gets transformed twice. Okay, once both as a local operation, once as a remote operation. Okay? And that makes kind of sense, right? We have this distributed merge being executed at both sides. They should be doing the same things, effectively, to converge to a common distributed state. Okay? So each transformation computed at both sides. And we must change the timestamps also, okay, to reflect what's really this operation now, what it is. The local buffer, the history, this is not like an undo history that never changes item. This is a buffer that keeps changing. That's why people didn't quite get it the first time right. So our previous control algorithm is given remote operation R concurrent with local operations L1, L2, Ln. Okay. For each L, R equals transform RL, execute R, etc. How will I change this now?
After execute the remote operation, we find in the local buffer whether there exists some local operation. The index is larger than the executed remote operation.
Okay. So you're saying we run this whole loop, we increment a timestamp. Now we go through and try to find some item in the buffer and we do what? I mean, you're talking of indices. This is a control algorithm. It doesn't even know anything about indices. It just knows about a transform function. It so happens that a transform function looks at indices, but let's keep our control algorithm independent of indices. And this function is looking at indices, right? Can we somehow use this function again?
Yeah, you can just do L equal transform L after.
Great. So effects of L1, L2, Ln included in R. Effects of R must also be included in L1, L2, Ln. Okay. Okay, I should make this superscript. We should also change the timestamp. Okay. So we say R equals transform RL, L equals transform LR, and L dot timestamp increment R dot site.
I'm a bit worried about having the way it's written right here is that when we call L equals transform LR, we are using like the now already transformed R as the input to that. And I can't convince myself that's not going to cause an issue.
Sorry. This is actually this is the previous R. So is it the latest R or the previous R?
We're calling it the latest R, and I can't convince myself that's fine. Maybe it is, but if transform is only ever going to be called in this context in pairs, transform could return a pair LR or RL.
Or we could just save the R.
Or we could save the R.
We should save the R and send the saved R here. Okay, so you're right. Okay, that this should really be okay. This should be the original R. So I think, like Nick said, he can't convince himself. That seems to be the safer thing to do. What you're saying is that they both can't get transformed, right? So we can argue that let's go and see whether we can make the more complicated algorithm to save this one step. Okay, so either R is the same as this R or not, right? If its index, if it is transformed, then can we argue that L will not be transformed? That both can't be transformed. It's a more complicated algorithm. I don't want to say that I'm convinced, just like Nick said, I can't convince. I think the safer thing would be to believe that this R is the original R. Okay, that we sort of run this in parallel. Okay, with indices and with inserts, I'm convinced. With inserts and deletes and priorities, I'm not convinced. So it should really be, I think when I give the algorithm, ultimately, I do a deep copy of L, R before I send it to the other guy. Okay. Any questions? Okay. For me to change this, there's a lot of places I've got this algorithm. So we'll just have you use your imagination to believe that this is the original. This is really a sort of concurrent kind of thing that's happening. Okay. Okay. Questions? By the way, should it be the original R or should it be the changed R? I mean, assuming it is the original R, this is an issue. But logically, what should it be? The transformed R or the original R? We want to include the effect of
Include the change by the local operations.
we want to include the effect of what? Confusing, huh? We want to include the effect of the remote operation on the local operation. The one that was received or the one that was transformed just now in this loop?
Intuitively, the answer seems to be you want to be the R that's received. we want to see how these two original operations transform each other.
Especially because I said the same transformation executed at both sides.
Right, especially since, yes, we want like both sides to see the same result, and we can't guarantee that if one transformation can affect the other transformation. But at the same time, maybe that is okay. Maybe that is what we want. It would take a number of experiments.
It would take a number of experiments or maybe some proof.
Or some sort of proof.
Because our the way we have written insert function, it's like R index greater than L index.
Yes.
And each time we change the index only by 1, so it can be at most equal to the index which is not transformed. So in this case, it won't happen.
Yeah. So if we don't consider priorities, if we don't consider deletions, it won't make a difference.
If we consider priorities in this case, both won't be transformed.
Yeah. So I think we can argue that one will be changed. Only one of these will be changed. But still, it'll be good to know. But that's a more complicated thing. That is saying that, we really want to take the original R, but if we change it, it doesn't change much. Okay. But should it be so you're saying it doesn't ever matter
Yeah, it will not matter.
in this case.
Yeah.
But we might have deletes also, we might have modifiers, and this is a transformation function that is a very general function. So it'll be nice to have some kind of proof here also, right? Without writing 15 pages on it, right? So okay, let's try to get a proof.
So,
Oh yeah.
I have a question. So, you mean in this algorithm, the later the R in the later transformation is the original R or the changed R?
Yes, that's the question.
The changed R or the range?
Yes. The question is this R, or this R?
Yeah.
And based on the fact that both sides have to converge, and it should really be the original R. But based on the fact that we want to take the effect of the remote operation on the local operation, maybe we should go and take the effect of the remote operation we are executing. But this is not the remote operation we are executing. We're going to execute some other R ultimately. So that argument doesn't seem to work. If we really want to take the executed R's effect, then we should be running the loop a second. We should be doing another loop later, right? So it seems that if we are going to go this route, it better be the original R at this stage.
Is that the original R at the beginning of each iteration of the loop?
Yes,
Or
or the original R that arrived.
Yeah.
Isn't this fun? How about each one of you implements a different variation, and we go through. This is not a funny. This is what people have done. There's one guy from France who's done exactly that. He says, you know what? I'm going to generate these workloads, and we just because this algorithm we'll get right, okay? But there are other algorithms we can't. There's no proof. We just have to rely on intuition. And he's been doing this work where he just feeds these things to these pairs of concurrent operations to various algorithms to see if anyone breaks. And he actually found bugs in published papers based on this kind of experimentation.
Okay. Actually, there is only one algorithm, right? The intuitive.
Okay, for 2 users, or there are many algorithms here also. For 2 users, just 2 users, they can be multiple. There can be multiple transformation functions. There can be multiple algorithms around the transformation functions. The transformation functions might make different guarantees. It may not make a difference here, whether we take the original R or the one at the beginning of the loop or the one at the end. It may just not make a difference, in which case they're all equivalent algorithms. Okay, but we need to know what's going on. But let's just go and see what's happening here first. So R equals transform RL. That's what happened here. It didn't change. So this algorithm doesn't show what's going to happen. L equals transform LR. Okay. So that's the one employ here. And we also change the timestamp here. Okay. So at least we kind of have an idea of what's going on. And we execute R. So I'm just showing you how this all relates to the example we just worked out before. Okay. And we increment the site timestamp also. Okay, so these are all these actions that we have to do. Now you can see why this is more complicated than your vector time step algorithm. And we haven't got to the main complication, okay, which is how to deal with n users. Okay, we kind of can deal with n commands. Okay, we still haven't figured out what this R should be. Okay, but we don't know how to deal with n users right now, and that's the complicated. That's a software engineering issue also. In fact, the paper that I use doesn't quite give you the algorithm for n users. I mean, it writes a couple of lines, but to work it out as an algorithm is tricky. And I've heard from one colleague of mine that Google Docs didn't get it right first also, or maybe didn't get it right, that it was Google Wave at one time, and he said every now and then they just synchronize anyway with respect to one user, just in case something has gone wrong. That was what he said. I don't think it's that hard to implement, but we'll see. Okay. So effects of L1 to Ln included in R, and effects of R included in L1 to Ln. Okay, let's try to go and figure this out through a proof of correctness. Okay. So our control algorithm is a slave of the transformation function. Assuming the transformation function is correct, our control algorithm must be correct. Okay. So let's go and say what our transformation function is really guaranteeing, so that we can figure out a control algorithm also. So given two operations, okay, we can draw the diagram this way. We start at state S. Both sides have to end at the same state ultimately. Okay? And can you guys try to interpret these arrows? What is this arrow going from S to S11 saying? All arrows are going southwards. Okay? Our states get changed downwards. Okay? So newer states are below the older states. Okay? The arrows either go southwest or they go southeast. They either go towards user 1, who's on the west, or towards user 2, who's on the east. Okay? So this particular arrow is saying what?
That operation 011 causes a transition from state S to state 11.
At which site?
At site 1.
At site 1. Okay? So whenever we execute an operation of site 1, at either site, we go westwards. Okay? And similarly, this is 021, goes from state S to S21 at site 2. Okay? Because 021 is executed without transformation. So it is the one that's executed at site 2. If site 2 issued it, then it is the one that's executed at site 2. Okay? Now, what's this arrow saying? That we're going to site S21 to S this state. Who executed this particular operation?
Site 2.
Site 2 is executing this operation to go nearer site 1 state. It's going westward. Okay? And what are we doing? Site 2 is executing site 1's operation done in parallel after it is transformed with respect to site 2's concurrent operation. Okay? So this is the function, this is the operation that's transformed, and this is the operation with respect to which we transform. Okay? Here, this particular operation arrived. It is the one that's being transformed with respect to 011. Your transformation function says, look, I guarantee you that 021 composed with T011 021 is the same as 011 composed with T021 011. That is what it's guaranteeing you. We can just forget about the indices. You know, that is something we have to work out from a transformation function. Okay? It's guaranteeing you that if there's one outstanding operation on both sides will end up at the same state because of what's being guaranteed. Our problem occurs So given two sequences of concurrent operations, transformation merge process can be derived. Our problem is occurring that we have two parallel operations here at site 1 with respect to, at a particular site. Okay, in my example, actually, I had site 2 have two parallel operations, okay, but it doesn't make a difference. So I have two operations that are parallel to this operation. How do I take, and I'm trying to employ a function that's meant for one concurrent local and one concurrent remote operation. I'm trying to use that function multiple times. I don't want to write every combination of outstanding sequences. Okay, two inserts and one insert and one delete and one delete. I mean, I'm happy to just write one insert, delete, 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 just pairs. Okay, I don't want to write all combinations where there might be n and is unbounded. Okay, I want to somehow apply these functions and compose these functions to handle the situation where I have n outstanding local commands and m outstanding remote commands, and somehow for them to work together. Okay, and we intuitively looked at that algorithm, and we still don't know what R that should be. Okay, so how am I going to apply diagrammatically? What do I have to do so that both of these sites converge to the same state? Given a diamond like this, I know the diamond is correct. So what do I need to do? After I've dealt with O11 and O21, and now when O12 I have to deal with, okay, O21 arriving at O12 or O12 arriving at this site, yeah, create another diamond. And how is the diamond created? I mean, is it created like this? How is it created?
From S1121 to the west.
Go here.
Yeah.
So basically, draw a perpendicular from here and continue this line, and then try to create a line that meets that, right? So whenever an operation from another site arrives, we are somewhere, we create a perpendicular from that to go nearer that site. Okay, so we need to create a perpendicular from here. Okay, and when these operations arrive, we create perpendicular from its state. Okay, and those two perpendiculars happen to be on the same line. Okay, so perpendiculars to meet non-dashed lines meet a unique point. Okay, so I go here, I continue this. This continues to be a perpendicular to this particular state, and I draw a perpendicular from there. Okay, and now what I have to worry about is what is the value here and what is the value here. Right? So let's consider, so what should be the value here? What am I doing? If I'm in this arrow, if I'm here, what am I doing? I'm at site 2. I have to consider the effect of O12 on my site. Right? So I have executed
Transform the previous results.
so transform O12 with respect to this operation or this operation. Okay. So, but I have to fill in, see, these diamonds are correct, right? So this O11 becomes O11 here. This O21 becomes O21 here. So O12 should be the first argument here, right? And the second argument should be this one. Right? So is the R the first R, original R, or the transformed R? We are doing TO12, right? We are doing the original guy. We are not doing this guy. Okay. Now, what should this value be? This value and this are the same. O21 is the one here. So the first argument here will be, and then with respect to, okay, that we already were doing. Remember that transform, that loop that we were doing? We were taking the transformation and then transforming it with respect to the next command. Okay, we computed one transformation, then we went and computed another one. Okay, one operation arrives from the other side. We transform with respect to the local operation first one, and then we take the transform result and transform with respect to the next one. That we were already doing. We were not doing this thing. Okay? Okay, let's go through this in. So multiple one-step processes to reach the state. Including effects of multiple locals on a remote site. So let's go and look at this first. Okay? Include the effect of multiple locals on the remote at site 1. Okay? So that would mean that O21 arrives at this site, right? Include the effect of multiple locals, O11 and O12, of a particular remote. So let's go and take this, let's go through this, the process we went through in slow motion, okay? So we compute this transformation, okay? O21 arrives here, we compute this transformation, and then we compute this transformation, okay? So effect of multiple locals on a remote, okay? That we already did, okay? Now include the effect of multiple remotes on a single local, right? So we take O11 and we transform with respect to O21, right? And then what we do is, okay, so we compute this value, then we have to compute not O12, O21, but O12, not this, but this. Right?
Yes.
Convinced? And when we were going through that loop and we had this remote operation that was being transformed with respect to multiple local operations, we transformed we basically, like I said, we computed this value and we also transformed the locals. Okay. And the local got transformed when we transformed O11, O21 with respect to O11, okay, we also transformed the local with respect to the remote operation. So it is the original R, not the updated R. Right? Because this is the transformation that we were computing. They were done in pairs. Okay? Questions? Okay. Same transformation computed at both sides. We'll go through the algorithm again. Great slow motion to figure out that R thing. Okay.
So that's a proof.
What do you guys think?
Yeah, I think it makes sense.
Isn't that brilliant?
More convincing.
More convincing. A guy called Matthias Ressel. He wrote a very complicated paper.
Oh,
Okay, and he was sending it to conferences. He should really, and which, anyway. So he came up with this. I've read that paper multiple times, and this part I'm convinced about. But there are other parts that when we go to end users that I never quite got, and I've tried to. It was just dismissed in a few lines. And there are people who understand this stuff better than me, and I've always asked them, how are you convinced that this works? Okay, and anyway.
So
But
like the three-user case require like a three-dimensional model.
And three-dimensional model, and he went to the n-dimensional model, and he tried to do the n-dimensional model in terms of the n-1 dimension thing, and that is the one that I never. And he did that like in 2 paragraphs, and I never quite got that. Okay. And I've talked to a lot of people, including him, and they're all convinced. Of course, yeah. Even I'm here saying, of course, right? When you do a proof of any kind, you just take some axioms and say, of course, right? So. But at least we kind of understand what's going on. Okay. So that's the whole point. The same transformation is computed at multiple sites. Okay. That's one thing. That there are some intermediate states like the one I just showed you that are never reached really. Okay. This is just to show you what's happening. But this state was never really reached. We didn't execute an operation reach the state. We executed the operation at the end. Okay, these intermediate states are only interesting when we want to do undo. Okay, and undo just creates a whole other messy, creates another can of worms in this whole situation. Okay. What if you have an undo and a local command executing concurrently? Okay, this just makes your, headache. Okay, so this is without undo. Okay, so now let's go and take this particular algorithm and see how it relates to this particular state. Okay, so include the effect of multiple locals on a remote at site 1. Okay, so O21 is the remote that we're going to execute now at site 1. Okay, so we've got this as the operation. For each L, which is the first L it's going to look at? O21 arrives at site 1. Site 1 is executed. What local operations? O11 and O12, right? It's going to look at for the first L, it's going to look at O11. Okay? R equals transform RL. Okay? What does that correspond to here? This one?
yes.
Okay. L equals transform LR. Where's that step? We need a TO11, TO21 somewhere. Or is it T11? So we don't even know which R it should be, right? Should it be this particular one? L equals transform LR, right? So what is the local operation? O11. So O11 should be transformed with respect to this operation or this operation. Are we transforming this operation with respect to this operation anywhere?
No.
No. Okay, but we are transforming this operation with respect to this operation. So this is right here. It's made the local operation come nearer the remote operation. So it is the original R. Right? Now we take the next operation in L, which happens to be O, 1, 2. R equals transform RL. So we transform O to 1 with respect to, we transform the transformed value, okay, T021, O11 with respect to the local operation O12, which is this one, right? And we have to transform the other way around also. We have to transform O12, transformed operation, right? Right? Now, the other part we've already done before, but let's go through that. Now, let's look at what happens when O11 and O12 arrive here, right? Given remote operation R, which is O11, for each L, which is O21, R equals transform this thing. So we do this transformation. L equals transform LR. We do this transformation. Right? O11, O12, we're doing both. We did that, we did these two transformations first at that site, now at this site, in opposite order. Right? Now we take the other operation, which is O12, for each L, which is now going to be a transformed L. Right? So this is this L now. And it's not the original L. That's what I'm trying to say. It's not O21 that we transform this vector, but T021, O11. Transform this. This is what happens, and not this, which is the mistake we made earlier. Okay. We transform, and we both reach the same state. Okay. Convinced? So now we have a proof. Okay, I mean, we have a proof that this is a wrong algorithm actually, the way it's written, because it's assuming this R is a transformed R. Okay, so we should really have the original R. Okay. Questions? So let's just go through our example. So now I'm going to take the deductive approach. Okay, I've given you the algorithm. Let's go and apply it to an example rather than derive an algorithm for an example. Okay. So here's our algorithm. Okay. So this particular operation arrives here. Its remote is not transformed, but did I transform the local one? Local is transformed, right? Then we execute it. We've got L in the beginning. Did I do it twice? Okay. Now I5 arrives here. Okay, it's become I6. So, and we compare it with this particular, but the local is not transformed. Okay, but its timestamp is changed. And now we compare it with the other operation. Okay, and I6 arrives here. We apply it as the at the question mark, as the exclamation mark. Right. Oh, sorry. We have to apply it now. Execute. We transform it and we get the question mark at this point, right? Just as we saw earlier. Okay. So hopefully this question mark, the exclamation mark here will come before this question mark. Second remote operation arrives at site 1. Okay. Lower priority. So this particular operation gets transformed. But this operation doesn't get transformed, right? And so executed and question mark arrives. Is executed here. Did I get this wrong? This site executed the question mark, right? So this should have really been exclamation here. I think I got the thing a little wrong there. Okay. Okay. So then the question becomes, what happens with end users, right? Will our current algorithm work with end users, you think? Did I ever tell you guys the joke about proving all odd numbers are prime? No? So a mathematician, engineer, and physicist are all trying to prove that all odd numbers are prime. So mathematician goes first, 3 is prime, 5 is prime, 7 is prime. By induction, all odd numbers are prime. The physicist goes, anybody heard this one? What does the physicist say? 3 is a prime, 5 is a prime, 7 is a prime, 9 is not a prime, 11 is a prime, 13 is a prime, 15 is not a prime. With an experimental error, all odd numbers are prime. And the engineer is supposed to be dumb. 3 is a prime, 5 is a prime, 7 is a prime, 9 is a prime, 11 is a prime, 13 is a prime, all odd numbers are prime. And then the computer scientist got added afterwards. And he wrote a program. And the program went, 2 is a prime, 2 is a prime, 2 is a prime. So by induction, we did it for 2. It should work for n users, right? We've got the algorithm. It didn't quite work from 2 commands to n commands. Hopefully it'll work from 2 users to n users. Anyway, we'll see. Okay, so where we left off last time was here. And let's put the laser pointer on. We came up with an algorithm, and we came up with a proof. And our algorithm initially was wrong. We didn't quite know which this R was. And we used the proof to figure out, to refine it. Okay? And the whole idea is that when you have a remote operation, R, that is concurrent with local ops L1 to Ln, okay? Then for each L, we transform R with respect to L, and we transform L with respect to R, both. Okay? And why do we, and we go do this in a loop. That means each local operation is transformed, and each remote operation is transformed as many times as there are local operations, once for each local operation. Okay, so what's happening in this diagram? That we start with some initial state, and we diverge on 2 different sites, okay? And then we have to converge back, okay? And when a new operation, so when we are at this site, we have to go towards this site. So we have to take the operation that was issued here, transform it with respect to the operation here, okay? So each time we go eastward, we are going towards site 2. Similarly, site 1 is going westward and going towards site 1. Okay? And if there are multiple operations that are queued up at a site, and a new operation O21 arrives, we want to first transform with respect to the first operation, take the result, and transform it with respect to the next operation. Right? That's what this loop is doing. That we go and transform R repeatedly, once with respect to the first operation, take the result, and transform it again. That part we got right, okay, initially. And then the issue was, we started also transforming L with respect to, there should have been comma here, with respect to R. Okay, and the idea here is that we are actually composing a bunch of diamonds, okay? And if an operation comes in, if 2 operations come in, from this site, O11 and O12. The first operation that comes in is transformed with respect to the local operation as it was issued by the local site. Okay, so O11 came in, and O11 got transformed with respect to O21, which was the operation as it was issued by the local site. Okay, when the next operation comes in, we want to take the effect of O11, the effect of O11 on O21, okay, which is this one, right? So, we're taking the effect of, this is always the operation that we're transforming, and so O11 was executed, so we take the effect of O11 on O21, okay? We take this operation and use that in the transformation rather than the original operation. That's what this L equal to transform LR is doing, that when O11 came in, we transformed our local operation with respect to that operation and used that in the function. Okay? So that's what this particular loop is doing. So, questions about this? Okay. This is what L equal transform LR is doing, that we, rather than using this operation, we use this operation here, and this question, the wrong thing here, this, if you remember from last time, this really meant that we are not using this operation directly, we're using this operation when we transform O12. When O12 comes in, we transform with respect to this operation rather than this operation. Okay, so everybody get that? Okay, so that's the subtlety here, that at each site, we compute both transformations. It's not that at site 1, we compute this operation so that we go towards site 2, and at site 2, we compute this operation so that we go towards site 1. We compute this at both sites. In one case, the local operation is changed, in one case, the remote operation is changed. And what is local for one site is remote for the other site. Okay? And that's why we have to go and say, transform RL and not change R, transform LR as before, and then later, before we go to the next iteration of the loop, we make R equal to RT, okay, so that we apply it again and again. Okay, so the way I presented it before, it was, I wasn't taking into account that R is being modified. Okay, questions? So this is what happened when we went from 2 commands to 2 users to n users. Okay, I remember I put a little question mark in my slide, so even that got lost. So what's going to happen now? Is the algorithm going to work? 9 is a prime. Okay, we can draw a diagram, but that's too formal. Let's do a little example first. Let's do it inductively a little bit. So what's happened here? 3 sites, lots of arrows. Okay, user 1 said insert A at position 1. Okay, in the demo that you saw, that's exactly what I did. User 2 said insert B at position 1. And user 3 said put C at position 1. Okay, now, what do we want to happen? There are 2 questions. Are all sites the same? Or and the other question is, what are all 3 sites? So it's got to be some value, but we should have a transformation function that gives us, that we can use to predict what the value should be. If there were only 2 sites, 1 and 2, what would be the value at both sites? How did we break ties? If both inserted the same position, site 1 and site 2?
We looked at the user ID.
User ID, and we basically said that the lower user ID has got lower priority. So the result would be what at both sides if there was just A and B? BA, AB? If one is lower priority, it should be AB or BA? BA? Right? So now, if assuming the same logic here, what should the output be? CBA. So we can prove that what went wrong. So we can either try to prove it using diagrams, or we can disprove it. So when you guys have to prove or disprove things in an exam, which do you prefer?
Disprove.
Why?
You should come up with one example.
Just come up with one counterexample. Right? Those are lovely proofs. So can we come up with a counterexample to show that that algorithm doesn't work? Can we either show that one of the sites will not get CBA, or show that two different sites? So we can disprove it many ways. We can disprove it by showing that one site will not have CBA. We can disprove it by showing that two sites have different values. Okay. And we can also disprove by saying that one site may have more than one result possible. Let's try the last one. Is it possible that, let's look at this site here. Is it possible that there's more than one thing possible here? CAB, okay, how? So these operations have been issued. We don't know in what order these are received. So this site is going to receive both the A and the B. What if it receives A first? When A arrives, it'll be 1, 1, A. Will the A get moved? It'll go to second position, so it'll become CA. When B arrives, will it get moved? It'll get moved. Compare 1 with 1. CBA. Pretty good. Looks like it's working. Looks like we can't have the counter example. Okay, so let's just go through that part at least. A arrives. Okay. CA. Okay. And I should actually update the timestamp here to 1. Okay. Oh, I do. Good. Then B arrives. Is compared with this one. So sorry, now B arrives. Okay. So it's put and it's compared with 1. And it becomes CBA. And I change the timestamp to 1, 1, 1. So far, so good. Maybe it does work. No? Why doesn't it work?
What if B comes first?
So what's going to happen? If B comes first, it'll get moved. It'll become CB. Then A comes, and it'll be at position. The B will be inserted at position 2, right? Now let's just go through that. So what was the symptom? What was something wrong? We never compared the ID of 1 and 2 ever, did we? We just compared the ID of C and B, but A was moved. So we never, that's something wrong. They were all at 1, and we never compared the two IDs. So that's why it's possible for something to go wrong. Right? So now we have a different sequence. First B arrives, right? Becomes I2B, right? We go and increment the timestamp, and we've got CB. And now when A arrives, what's in the local buffer? Is this particular operation. B is not in the local buffer. Maybe there's something wrong there too. Right? But we don't put remote operations in local buffers. We only put local operations in local buffers. Right? So A comes in, it's compared with this, becomes 1, 1A. Becomes 1, 2A, and we have CAB. Counterexample. So we can all go home and say, okay, we can prove that's wrong, but hey, we want to implement this stuff. We don't want to give up on end users. So what's going wrong? So it didn't work out. We didn't store the value of remote operations in local buffers. So lots of bad things are happening. And I'm not sure why I'm flashing these again and again. I guess I just updated the timestamp at this point. So order of concurrent message influences the output. We see that same output is not guaranteed at a single site. So that means same output not guaranteed at all sites. Right? So that's our proof. And so I'm not sure what I'm trying to say here. I guess, transforming didn't help us. Okay. And let's look at a state diagram and say that why does that state diagram not help us here?
I think before we had two users, there was this assumption there was us and there was this other.
Right.
And messages from the other were all coming from the same person, so they were always coming in the same order.
So there was one other person.
Yes.
And
so, like when we're looking at the diamond diagram, when there's one other person, there's a definite order to operation 1, then operation 3, then operation 4, and that allowed us to construct this diagram.
Okay. So certainly operations from the other side are arriving in order. We can always assume that operations from the remote side arrive in order. Right? All right. Okay. And there's only one other site. So when there are n sites, the trouble is that what is not in order?
The sequence of all remote messages.
All remote messages not on. That means that there are, and remember what you said last time about this diagram being generalized to the N3 user case, what would happen?
That it might be a cube.
It might be a cube. That's another way of looking at it. That it's not as if, there's one path here and one path here, and we're working in a 2D plane. We're now working in a 3D thing. And we can diverge along multiple directions, and then the diamond gets replaced by now a cube. Right? So you go from one end of a cube diagonally opposite to the other end of the cube, and there are multiple paths now to go to the end. Okay? Whereas in this diamond, each site has only one path to go to the convergence state. Right? This site has to go here, this guy has to turn left. When there's a diamond, each site can go to the converging state using more than one path. And unless we guarantee that going through all paths is the same, we are in trouble. Okay? So 3-user diagram is this, that you're at this particular state, S. Okay? You may have executed O1 as site 1, another site has executed O2, and yet another site has executed O3. And what we have to do is take all 3 operations into account and come to this state. And there are multiple paths. You can go, how can you arrive at this state here from this state? What are 2 paths? So let's say I can execute O1, right? Or there are actually not just 2 paths, there are multiple paths. Okay? I can go here, and then here, or I can go here, 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 Many paths. Okay? And the question is, can we guarantee that regardless of what happens? Remember, for two-user case, we had a correctness criteria. That TO1, O2, O1 is the same as TO2, TO1, O2. Right? If you execute operation T1 and operation O2 comes in, okay, then when you transform O2 with respect to O1, we get T1, O2, O1, and that should be the same as TO2 and then TO1 transformed with respect to O2. We had a correctness criteria. Now we have a much more complicated correctness criteria. And our transformation function, we saw, didn't work. That it was not as if along all paths we got the same answer. Yes, we had multiple paths, we saw that, and our transformation function was such that the two different paths that were taken at a particular site didn't yield the same answer. Okay? So let's reason this out. So path for user 1, let's say user 1 has executed O1. They can go to this state either this way, right? That means, what does that mean? First we go in, and then first we go towards the O3 guy's side, then we go towards O2's side, right? Or we can go, right? The two paths must give equivalent results. Okay, that was what was going wrong. Okay. In our example, our transformation did not give us that same result. That was the problem. Okay. So what are the necessary conditions so what we can try to do and what people have done and spent a lot of time on is come up with appropriate transformation functions. Okay? And they did that without this diagram first, and it was all confusing. They said, oh, you know, that I didn't work with, let's go and change this to this, and it seems to work now. That example that, you know, an example that didn't work now works. Okay, so it was proof by example rather than proof by counterexample. Right? And then this guy, Matthew Wessel, came up with this thing and said, look, there is a certain condition that your transformation functions have to give you. And the reason why they're not working is because that condition is not being satisfied. Okay? So basically, the way you want to look at it is that this is wrong what I'm saying. So when each edge has a unique label, okay, when you can come to that edge only from one path, things are easy. When you can reach an edge from more than one path, then that edge can have more than one label, which label is, you know, the T, the transformation function that's applied. And what you have to make sure is those transformation functions are equivalent. Okay? So that's the way to look at it. So edge can now have multiple labels, and the labels should be equivalent. Okay? So let's go and see this. So we are trying to go here. Okay, I just flashed this. I noticed that my flashing is not that, you know, maybe I should use thicker edges here. So how will you label this one if we are going from here to here? We want to take the effect of O3, assuming O1 has been executed. So this should be T what? T03, O1. Okay? Now we want to go here. Right? So we want to take the effect of O2. We want to execute O2, assuming this operation has been executed. So we want to transform O2 with respect to oh, sorry. I guess I'm going here. Right next. Okay. This is the easier one. Okay. So O1, I should have seen it flash. You know, I did flash everything, but I just can't see them sometimes here. So here, what are we doing? We are saying that we are at this state, and we're going to go and execute O2, assuming O1 has been executed, so O2, O1. But this is the easy one. And now we are flashing that one, and it is TO2, TO3, O1. right? Okay, so did we get this right? We've computed this value first, okay? And now we are going, we have to take the, we have to execute this operation, assuming this operation has been executed already.
We have executed T0301, right?
We have executed 0301.
And now we want to take the incoming operation, that is the
So we want to take O2. O2 is effect, right?
Why do you need to do the O2 on top of O1?
Okay, so let's get this right. Okay. When we took O3, we did T0301, right? That was fine. And we are going along this path. So we are going along this diamond, and we know that each diamond is correct. Okay, so this particular edge is adjacent to this edge. So this is fine. Now I want to take the effect of O2 on this particular, on where I've reached here. Okay? This particular edge is not adjacent to this edge. But I have this diamond to worry about. I have this diamond. So I go, and that is the step that I missed out. Okay, I made the same mistake that you guys are thinking. Okay, so I have to first go and find this edge. Okay, because I've got this diamond. This is not part of a diamond here. This is part of a diamond here. So I first take the effect of O2. I first take transform O2 with respect to O1 so that I reach here. Okay, and now I can compute the effect of this O2, this transform operation, on the operation I've executed. Right. So I'm at this point. This point is not a part of any diamond here. So I go and fill up this edge. And now this is part of this diamond. Okay? And this is the operation that is the incoming operation. This is what I've done. I transform what the incoming operation is with respect to what I've done. Right? And now if I'm going to go here if I had done this instead, if O2 had arrived first, and then I was to take the effect of O3, what would I do? If this is the one that had arrived first, and now I'm trying to take the effect of O3, so I have to do O3, O1, which means I have to fill this particular part. Right? So let's just see what my animation is going. Okay, so now that I've done this, so now when O3 comes in, actually when O3 comes in, I go and take, so this is what I have executed, right? And T, O2, O1, so let's see, so this is just filling up the diamond, this is just filling up the edge, the other way around. Right?
Yes.
So this is saying, this is the reverse of this, right? So we've got this label. We've got this label now. Okay. This is assuming that we have executed this operation, and we are trying to execute this operation. Then we transform this operation with respect to the operation that's been executed to get this. Okay, so we've got this label here, and we'll see that this edge will have more than one label later. Okay. Okay, wait a minute. Okay, now we're trying to do other ones. So we have executed O3. We have executed O2. Now we want to execute O3. So we do T03, O2.
Yes.
Right? T01, O2. This is just follows from this. we have executed O2, and we are trying to take the effect of O1, so we transform O1 with respect to O2, right? So we fill this part up. Now, what is this value going to be? We have executed this operation. This is the operation whose effect we want to take. So this will be what? All right. So this will be the first argument. This will be the second argument. Okay. And now that we have executed this operation, and we want to take the effect of this operation, what will this label be? You want to transform this operation with respect to this operation?
Yeah.
Is that right? This is wrong, right? Is this wrong?
I think it's right. It's right. So
Sorry. We have executed this operation, and we want to take the effect of this operation. So it's just the opposite of these two arguments. Sorry. Yeah. Okay. So this edge has two labels. That means for this particular thing to work, these two should yield me the same answer.
yeah.
Okay. So this was our transform constraint so far. That we had O1 T1 O2 O1 should be equal to O2 T O1 O2. That was the constraint, so that each diamond works, right? And now for the cube, we have to have this constraint also. So these are called the TP1 and TP2 conditions. That each diamond should be right,
Yeah.
and then each cube should be right too. So we've got the condition for 3 users. We can just go tell the community, go design your transformation functions to do this. And that has proved to be really hard. Okay, the other thing is, before we go to that, we had one buffer originally for our local operations. Will that work now? We kind of saw that, right? When the operation came in, when the operations came in, we hadn't taken properly the effect of other operations into account. And intuitively from this picture, why do you think one buffer may not suffice? What are we doing in the buffer? We are storing the effect of an incoming operation on the buffer, right? We are computing these functions. If we are at O1, if we've executed O1, and O2 comes in, we transform O1 with respect to O2 in the local buffer, right? Of O3, and if O3 comes in, we have to transform with respect to okay. So we compute these edges, and now I might either be doing this, I might be either going through this path, or I might be going through this path. That means the transformation functions I compute, I have to compute 2 different transformation functions, depending on what path I've taken. The same transformation is not going to apply across all paths. So that is another reason, that's another complication here. That you can't just assume a linear buffer. There's more than one path. So you have to compute multiple, you have to have multiple buffers depending on what operations were received. Okay? And we can go into complications of how to do that, except that, I'm just going to say it's. So to better understand why a linear model doesn't work, let's unclutter this picture. Let's look at the local buffer. And suppose that O1 is executed. So O1 is put in the local buffer in case there's a concurrent operation later. The concurrent operation is O3 assume. So O3 must be transformed before applying. And we must take the effect of O3 on O1. So we replace O1 with T1 O3. Okay, so O1 has disappeared. Now let's say O2 is executed. We know we must compute this transformation. And for that to happen, we need O1 in the local buffer, and O1 is no longer in the local buffer. Okay? So essentially, we must remember that we took this path and then this path to compute this value. And had O2 been executed after O1, we must remember that we took this path and then this path to compute the values for O3. Okay, so this shows you why a linear buffer no longer works, and we need something much more complicated, which is what Russell calls an interaction model. Okay, so there are multiple concurrent paths from a vertex, and you must essentially store the path. Really hard. Okay, before I even go to that, Matthias Russell, who came up with this paper, this is just for the 3-user case. What happens to n users? Well, Matthias claims in his paper, and everybody who really works in this area tends to agree with him, but I don't understand it, to be honest. He says this is sufficient for n users also. He says by induction. Okay? Given TP1 and TP2, it recursively applies. That's what I always hear from people. It just applies recursively to n users also. Okay.
So it's kind of proof method mathematics.
That's all he says. It's a conference paper. It's not a journal paper. Okay.
So
And
they don't work out the proof. They just say, oh, it's intuitive.
It's left as an exercise.
Yeah.
That particular paragraph has given me a lot of headache. I've tried to read it many times. And they're both, I know him, I know the other guys who worked on it, and I've just sent emails, and he says, it just works recursively because you've got TP1 and TP2, and it might. There's some insight there that I'm missing. Like I said, I haven't really designed an OT algorithm in my life, except, the ones that we've done based on the papers I've had to fill in details. Okay. But we can go through and make our head ache whether this is sufficient or not. Or you can say, look, if people can't do it for 3, okay, so claim TP1 and TP2 sufficient, creating functions meeting TP2 has been problematic. Okay? Given that, why rack your brain about whether this works for n users or not? If you're a practical person like me, you're saying, okay, yeah, in theory, maybe this applies to n users, but in practice, even 3 users has been hard. So it's not that not such a practical issue. Okay. Okay. So what should we do now? Just not allow multiple people to edit the document together? Some people claim that this is editing is something that you can't have multiple people doing. It gets very confusing. But if you've got a status report, and I'm entering my part of the status, you're entering your part of the status, that's a common example application in Google Docs. You probably want that to happen. So, so what do you think Google does? And I use the word Google. This is not Google's algorithm. Okay, This algorithm I'm going to talk to you about was invented in the context of a system called Jupyter by 3 people, 2 of whose names I know because I know them. They were working in Park Place, Xerox at that time. And they published a paper in 1995 conference, okay, which I had a paper too, so I sort of saw that presentation. And you guys know about AFS, the file system. And anybody at UNC you know who has worked on AFS? Don Smith. Okay, and the AFS paper has Don Smith and a guy called David Nichols. And David Nichols was one of the authors of this particular paper. And I talked to you guys about MUDs. And MUDs was a lot of people in Xerox contributed to MUDs a lot. And one of those guys was a guy called Pavel Curtis. And after David Nichols graduated from CMU, he went to Xerox. And I forget where Pavel graduated from. And these 2 guys and another author whose name I don't remember came up with this paper. Okay, and they also had a very brief description of the algorithm. So we're going to fill in details. And those are the details I was filling in that I couldn't get synchronized today. So, but I mentioned Google here because Google uses a certain philosophy about where it does distributed computing. And can you imagine just what that philosophy might be that could solve our problem here? That we somehow go from 2 users to n users in a more understandable way. Yeah.
Well, Google has like a centralized record, doesn't it?
It has a centralized server. Everything is, you've got web browsers, we've got servers. Okay? So we're going to make use of servers. Forget this n-way P2P. I'm not saying forget this. Okay? There are algorithms. Okay? But I can't describe those algorithms to you because A, I don't understand them, and if I don't understand them, I can't describe them to you. Okay? What we're going to do is put a server in the picture. Okay? And we did this before, right? We said let's have synchronous atomic broadcast. I send my action to this relayer. I don't do the action on my local buffer. And it comes back to me. It echoes back to me. So we are all guaranteed to have one path, which is what Nick was talking about. Everything is now being done in the same order. And what was the problem with this approach? Do you guys remember? Okay, so do you think Google does this? There's a delay. Right? And do you think when you type in Google Docs, it's going back to the server and going to the server and coming back? You don't know. Might be. Maybe your server. And what was the other problem with this? Delay was one problem. Let's say we have really fast networks. The same problem undo also has.
Yeah.
What's the problem?
The PC1 undo it at the same time PC2.
No, forget that there's undo going on. That's just even more complicated. Let's not even get into that. But I'm saying, forget undo in concurrent case. Think of undo in the single user case. And I talked about a problem that occurs in the single user case with undo if we don't undo the last command. Does that trigger something? State of operation issue not the same as state of execution. When this comes back to you, some other operation might have arrived. Right? So if I2U and I5 is the order in which the operations get serialized, we get this result, which is not the intention. And we saw that if there were deletes around, we would even get exceptions. Okay? So we want to use a server, but not in this way. So how could we use a server and yet somehow our work from 2 user to translate to the end, somehow have induction finally work? at least in a way that we can understand. We don't want this to happen. We don't want the delay. We don't want we don't want an intention violation. Yet we are going to somehow use a server to solve our problems.
Yeah, I mean, you also, when you want to send everything to the central server, but you also want the server to know what the context the action was done under on that individual peer.
Okay, so we're going to send everything to the server through the server. The server has to know what was done by the individual peer. He's not just a regular relayer. Is this like some other server you guys might have used before in team software engineering? So what happens in Git? When you do your local changes, do you have to be even connected? So what do? You do your local changes and then you merge them with every one of us, or you merge them with everybody merges with the central server. So everybody's consistent. That's the key. Okay, we'll just do it in real time. We'll do our local action. We'll somehow have the server, we'll have all these actions go through the server. The server must now have some state. And we'll just make sure that each individual is consistent with the server, and by induction, all clients are.
Don't you still have like a race condition that can happen? If you think you're consistent with the server, because you're understanding that the server has changed.
Okay, so can you have a race condition with the server? We have a two-user OT algorithm that we're convinced works. That takes care of the race condition with the server. Right? Simple? Okay, so what are we going to do? We are not going to do synchronous relayed broadcast. We're going to do a local operation, send it to this relaying merger now. We send it to the other operations. We send the operation to other clients. It may or may not change that operation. It may transform it actually. Okay? And that's the key. That things are going to other clients through the server, and we are trying to just make sure that there is some state, logical state in the server with which we are consistent. And if we are consistent with the server, then if A is consistent with the server and B is consistent with the server, then I guess it's not induction, it's the associativity rule, that then all of us are consistent. Right? So we are going from 2 to n users. We're not trying to do n user merges at each site. We are doing n 2 user merges essentially, where we are one user, and as far as we are concerned, the server is the only other user. Okay? Through a server, each client is consistent with the server, implies each client is consistent. Implies each client is consistent with each other client. Right? This is the associativity rule, if I remember my middle school or early school mathematics right. Okay? So that's what the Jupyter. Jupyter was actually a system. It was not, the algorithm was like one section of it, like half a page almost. Okay? Maybe they gave an algorithm too, but it was not, they had a whole full system in there. That's why it's called Jupyter. I mean, there was a system with an algorithm. But the server does not issue any operations. So what does it really mean? to be consistent with the server. When we know that this guy's issuing an operation, this guy's issuing an operation, I'm site 1, he's site 2, I got a timestamp here, he's got a timestamp there, we know whether we are concurrent or not. What's the server's timestamp? How many elements does the server's timestamp have? And if the server is the other user, then what are the operations executed by that user? So if I'm user 1, and there's user 1, 2, and 3, from users 1's point of view, what are the server operations?
The server's operation is send the operation to user 2 and 3.
So the operations, the other user's operations from the point of view of user 1 are what? Say that again?
From server send to user 2 and 3, other users.
From server sent to users 2 and 3, or because if I'm user 1, my operations are going to user 2 and user 3, right?
Yeah.
So my operations cannot also be the server operations.
Receive the operation from user 2 and 3.
Operations received from user 2 and 3. If I'm user 1, my other user operations are operations received from 2 and 3 by the server. And if I user 2, 1 and 2, and so forth. Right? For each client, server operations are those issued by other clients. Okay. So this is essentially what the Jupyter paper said. Okay, that your timestamp has got your two bits. Either you can consider that to be local, consider that to be client server, or local remote. Okay, and actually it gets a little confusing because if you consider as local remote, then what is local for one side is remote for the other side. Okay, if you consider as client and server, then they're consistent, but then there's other issues. So I think in my slides I consider local remote. Okay, so remember this, that one guy's local is the other guy's remote. Okay. So let's go and look at a picture. Okay. Okay, so I didn't, this is where I've lost updates. Okay, let's see. Maybe it's just an animation issue. So you all agree that there should be a local buffer each site. There should be a timestamp. And let's see what happens here now. I have no idea about how the animation is going to go because I don't know whether this is what I ended up with or not. Okay, this is when I started losing. This is where I don't know at what point I lost changes after they got synced. So my timestamp here, my local timestamp is the number of operations I issued. And my remote timestamp is telling me the number of operations issued by 2 and 3. Similarly, okay, so let's see. Okay. And this, right? So we know what our local timestamps will be. Okay. What about this merger guy? What kind of data structure exists there? Does this merger have any buffer? Does it have a buffer? Why does he have a buffer? Our OT algorithm demands a buffer, right? as was mentioned, that there may be race conditions between the server and the client. If you're going to employ an OT algorithm, we better have local buffers at both ends to take care of the race conditions so that we can transform and go along the diamond and converge. Because they're not doing synchronous actions. User 1's doing an action, user 2 is doing an action, that's equivalent to the server doing an action. We have to somehow go and transform at both ends. That's what the algorithm requires. So, one buffer? Buffer per client. Because I'm masquerading as 2 and 3 for 1, as 1 and 2 for 3, as 1 and 3 for 2. So I need to have a buffer for each one of them. So then how many timestamps am I going to have?
40.
Where n is equal to? Okay. For each buffer, I need a timestamp. Separate local buffers. And this timestamp, again, I flipped these two in my algorithm, and please, in your implementation, flip them. Okay, you'll have to do some flipping because what is local for me is remote for the other guy. Okay, so this, I'm assuming this not client server, but local remote. Okay, so this is my local operations, and these are my remote operations from the point of view of this user. Okay. Last time I've given this the implementation once before, and it was ambiguous whether this is local, this is client server or local remote, and they didn't flip. Some of them didn't flip, and they got into real trouble. Okay, so now in my tracing, I have flipped, okay, as a case, just to make sure that you flip. Okay. So it all makes sense? Okay. Let's say this guy issues an operation O. User 1 issues an operation O. What should happen now? It's going to go to the server. What's the server going to do? Okay, update. So the message should go to some buffer, or one or n or n minus 1 or n minus 3, we don't know. Some set of buffers it should go into. And the operation has to go, it has to go to the other guys, right? And some timestamps should also be updated. So the timestamps, so which timestamps should be updated? All of them, right? Okay, that's good. And then which buffers? Or buffer. Change this buffer. Put it here. So I certainly put the operation in this buffer, right? I update my timestamp here. I do that. It arrives here. I should update this timestamp, this timestamp, and this timestamp. Before, at the end of everything, that should have happened. Okay? So what do I do first now? Buffer it in 2 and 3? So the operation just goes and then send it to these guys?
Yeah.
So I don't run any OT algorithm here. Certainly I ran an OT algorithm here, right? When this message arrives here, it'll get transformed with respect to this guy. No OT here?
Transform with respect to
So-
local buffer 1, 2, and 3 times.
Okay. Transform it with respect to with respect to,
Yeah.
no, but you always transform it with respect to some operations. So which operations should I, there are operations here, there are operations here, there are operations here.
He transformed according to the local buffer 2 and then send it to, and then transformed according to 3 and then send it to 3.
Okay, so what you're saying is, I should transform this with respect to the operations
Yeah, stored in the,
in this buffer and send it to this guy.
yeah,
Transform it with respect to the operation here,
yeah, understand.
send it to this guy. And then I put this operation where? I should put that in some buffers also, right? You didn't like that. So before we say why you didn't like that, where should I buffer this guy?
Yeah, so sorry, it should transform according to the buffer 1 and then buffer this transform to buffer 2 and buffer 3 and then send it to.
Okay, now you like it. Okay. So I transform this operation with respect to the operation in this buffer. I compute some transformed value. And I send it, and then what do? What buffer should I put it in? This buffer? 2 and 3. 2 and 3 will have operations. 2 will have operations executed by 1 and 2, 1 and 3, because the local buffer is that. That's the servers pretending to be the sum of the other clients. Okay? This part was not given in that paper. Okay, it was left as an exercise, and so this part, I mean, so there could be something wrong here. So please look at it very carefully. Okay, and I've been told that I told you that Google just periodically synchronizes the buffers just in case, and I found an implementation in with Eclipse multi-user editor, and they say that. I mean, I see the command there that they also use the Jupyter algorithm. They say as it's implementation provided by some particular site. They go and refer. And they say, but we do all synchronize every now and then. So, like I said, this has not been reasoned out formally in an accepted paper as far as I know. Okay? So let's go through this in slow motion. I go and increment O1, 1, that's what this flash right now. I put it in the local buffer. I go and compare it with the operations in this local buffer, right? After I've run through all these operations, I've got an OT. So I didn't put it in this local buffer. I just transformed it with respect to these operations. Okay. I update the timestamp for 1 there, right? I now update the timestamp for 1 here. I put it in the local buffer here. I similarly do it for the other guy. Put it in the local buffer there. Finally, it gets transformed. Then when the operation arrives here, it gets transformed with respect to the operations here. And I compute some transformation of the transformation. First transform with respect to these operations, then transform with respect to these operations. Right? I update the timestamp. Similarly, I do some other OTT. This is, it's done with respect to another set of operations. So these two are not the same result. Okay? And I update the timestamp here. Should work? Because I'm trying to basically, even though I have not stored the buffer anywhere here, Google Docs, from what I've heard, and this other system that I've heard, they actually store a copy here. And every now and then the clients all make sure that they're the same as the server copy. I have done no storing here. Okay, I'm just relaying them by transforming the operations. I mean, I'm storing it in the buffers, but I do not don't create a copy of the sequence as the master copy. Okay. Questions? So what are we doing? We had a client algorithm of this form. Okay, for each, this comma is missing here, and this n is not a superscript here, so I'll have to change this everywhere. I'll try to remember. How will the server algorithm change from this? Okay, by the way, these are the receive algorithms. Huh? This is not the send algorithm. The send algorithm is what, you go and update the timestamp, put it in the client, and send it across. Okay, this is the receive algorithm. So when the server receives an operation from a client, right? It goes and finds out for each of its local operations with respect to that client. It transforms it, does this.
Yeah.
And any other change?
So execute
What should this be replaced by?
store into other buffer and send it to other client.
Or just send it to other clients. The send will go and store it in its buffer. This is the receive algorithm. So just send to the other clients, and those clients will do the necessary masquerading it as a particular user. Okay, and those guys will each will go and store it in a separate buffer, hopefully. Okay, we'll look at the data structure for that. So server algorithm. For all other sites, assume server executed R. Basically, that's what you're doing. We don't really execute it, but for all other sites, we assume that it executed. Okay. So we have, how many OT managers will we have now? In the client, how many OT managers will there be? You guys had a causality manager, right? So similarly, we'll have an OT manager now. And how many will the server have? N, right? So there is one OT manager, there is this OT manager for this client, and then you go and send it to the other clients through their OT managers, using different OT managers now. Okay. Okay, one other issue. What about this business here? The transformation function. We were using the same transformation function everywhere, right? Now we are going to have local and remote. I mean, so what's going to happen if both insert the same position? Which is going to win?
The server win every time.
But this particular guy doesn't have a notion of server. So we have a little problem here. As long as the timestamps were client and server, we were fine, but I made it local and remote. Okay, and this is the confusion I had. I kept changing my code also at times. So somehow we have to know that it's so what would you like? The server should win or the client should win?
Like the server wins.
Why do you like the server winning?
I mean, it's more likely to agree with more people.
No, we'll get consistent results. Won't we get consistent results either way?
Yeah.
Because we are doing these end two-way mergers.
I think, well, if I'm typing in a block of text and I start to receive messages from the server, I don't want those insertions to break up what I'm writing.
Okay, so you want
And my gut is that if the client wins, if the client gets priority in this, then that won't happen. But I'm not going to prove that. So.
Yeah, if two people are typing, one's going to win and one's going to lose.
Okay, fair enough.
You know, so it's not just, remember, the server is not issuing anything. So the question is, if I typed and you typed, which one of us should win? And if the server is winning, what does it mean? If I typed, I put A and you typed B, and the server wins,
Then it means you win.
who's the you?
Whoever's closest to the server. Whoever can get to the server the fastest.
Fast.
Yeah.
The earlier operation wins. And can you argue that that's the right thing? Yeah, if we are entering stock codes, well, is that the right thing for stock codes though? So maybe the later operation should win anyway. So what you have to do, and what I do, is that in the operation, I store whether this is at the server or the client. Okay, so not only do I go and flip the indices, I go and also put a little flag there saying I'm at the server right now. I use the same transformation function at both ends. Okay, but I put a little bit there that this is server, and I say if this operation is being executed in the context of the server, then increment the index. Okay, then you lose. Otherwise, and you could go either way, and it should give the same results. Okay. Okay, I thought I wouldn't finish 1 hour, 15 minutes. I was working for four and a half hours today, this morning. So and I started with some slides I already had. So it's good that I got through so far. Okay, let's go and look at the architecture quickly. Let's not. Well, let's look at it because you'll get an idea. So you had a causality manager. Okay. What will happen in the case of OT? In terms of the architecture, you now have an OT manager. You had one causality manager per site, per client site. And you guys earlier said that there's only one OT manager per client site. I'm going to argue there can be multiple OT managers at each site. Think of your application. Causality manager, does that ever look at the contents of the message? Does the OT manager look at the contents of the message?
For each field.
For each sequence. Okay. One for each sequence. One for each transformable data structure. In our case, that is the sequence. Okay. What about the server? Firstly, you guys don't even know how to put a server filter. You know how to put filters at the client end, the server you've been just executing. Okay? And the server, but there's a way to do it. And that's the way that I've entered 2 times already today. Once on my desktop computer, once at a home computer, but it's not here. So we're going to pretty much end right after this. How many? So now, where that was, this is a relayer now, and there's an OT unaware communication system, OT unaware relayer, and we want to go and put some filters in to add transformation. Okay, so basically you're going to take my code, my server, embellish it, add some application-specific OT stuff there to make it work. Right? So that's the idea. Let's go and carry on. Okay, so this is where we left off. We were looking at the architecture of an OT system, and we need OT in our central merger at both the client end and the server end. Okay, and this was the architecture at the client end. This architecture is very similar to the architecture we saw with causality, and the goals were similar. The idea was to keep the application unaware of consistency, the communication system unaware of consistency. In the case of causality, we added a causality manager, which share the data structure between the receive and send filter. And in the case of OT, we have an OT manager. Okay, but still we need these 2 filters from software engineering point of view to decouple these 2 components. Okay? And one difference between causality manager and OT manager is that causality deals with untyped messages, OT deals with typed messages, with state, and we have a separate OT manager for each transformable object, and we're just looking at sequences. So it's required for each sequence, and in your project, that means for both the editing buffer and the message history. Okay, so that's the client architecture. And this is the server architecture. Again, we have a OT-aware communication system. We also have a layer that is producing and consuming messages that is also OT unaware. Okay. And this layer has been written by me. So it's even more important to keep it independent of OT, because if you went and integrated the OT code into this relayer code, then if I later was to update the relayer, you would have to copy and paste the code. Okay. Now, one difference between the relayer and your application code is that it does not generate messages autonomously. The messages it receives are the ones it sends. Okay, so we really don't need two different filters. We can just use one filter for a particular application, session, pair. Okay. So the question is, which one do we choose, receive or send? And we could do either. As it turns out, the receive filter does not know which destinations a message may go to. Okay, if the client says send all, then it's a relayer that knows how to translate all into specific addresses. The send filter may also not know. If it is called before the message is multicast, then it also wouldn't know. But if it is called after that, then it would know. Okay, so if it does know, it would be useful to go and it would make the code easier to put the OT code here. As it turns out, in this implementation that we have, the send filter is given the multicast message. It's not given the unicast message. We'd have to generate unicast messages from the multicast message, so it doesn't make a difference. But we'll just choose the send filter in case the design changes later. Okay, so the receiver immediately sends. It doesn't really execute the messages. This code doesn't really do any execution. Okay, it's just a conductor of messages. We can use only one filter. The send filter is more flexible in general, so we're going to use the send filter. Okay, but in this particular case, like this says, in this implementation, it doesn't make much difference. It's simpler in that sense, in terms of filters, it's simpler to the client picture. But of course, the complication is that we need not only an OT manager for each sequence, but for each client, because of the implementation we saw earlier, that we have to pretend to be, we have to take a different form for each client, and that requires us to create multiple buffers and multiple timestamps. Okay, so that's the main concept here. After that, it's mainly details, which is how to attach send filter to a server. And we saw the message filter interface for clients. We need similar capabilities in the server also. We need to know who to forward the message to, and we need a method to trap the messages. One difference is, filter actually is an extension of this particular interface. And the reason is that in the case of the server, we need to create a separate OT manager for each client. So we need to know when clients join and leave. Rather than worrying about how to do this, how to trap these events in the server, which you don't know. I've provided these two methods in the filter itself, so that you can maintain your data structures. Okay, so this is the filter. We know that filters are not instantiated directly by factories, and factories have interfaces too. So this particular factory returns an object of type server message filter. And we also know that to choose between different factories, we have an abstract factory, and that's what I call a selector. And by default, it just forwards the message, and you will replace this factory with your own custom factory that will create the OT manager. Okay, so this is pretty simple, and it follows from what you've seen already in the causality case. So now we know how to write a send filter for the server also. Okay, we knew how to write it for the client end. We knew how to write both send and receive filters. Now we know how to put the send filter in the relayer. Okay. So the next question is, how do we? So we know how to. We know the architecture. We know the basic algorithm. Let's now look at the detailed algorithm with the traceable steps. and we want to see that both for the server and of course, one complication that I'm going to give you in assignment is to create a separate OT system for each sequence, and just to make your life easy, we'll actually look at the algorithm I'll show you assumes that we do have multiple sequences, so that task will become easier. So to make sure our task isn't too complicated, we'll make sure that the OT manager is shared between both the client and server. The filters cannot be shared. We saw that this architecture is asymmetric. In the case of the server, we have only one filter. In the case of the client, we have multiple filters. And that filter in the server is acting as both a receiving and sending agent. It has to do with multiple users. So we'll share the OT manager. We'll have multiple instances of the OT manager, but the filters will not be shared and they'll be more complicated. Okay. So in the causality algorithm, I never gave you the algorithm for the causality manager. I just gave you the algorithm for the send filter and receive filter, and what was put in here just followed. It was fairly simple. Now I'm going to actually give you the interface between these filters too, between the filter and the manager also. And hopefully that won't constrain you too much. Okay. So multiple sequences, we need to create for each list a separate OT manager. Okay, so that will make our task much easier. We just have multiple replicas of the OT manager, one for each list. Multiple instances, I should say, they are not kept consistent. And then we create the data structure in the beginning. We assume in the beginning we know every list that we have to handle in the client. Okay, we're going to first look at the client, then the server. And we create a new OT manager. We pass it the client name, and we also pass it an argument that says whether it is a server or not. Okay, and these two arguments are going to be useful for tracing, so they are provided to the OT manager. Okay. So we store this OT manager in our table, which will be a hash table, and in initialization, we also create the receive and filter factories, and these factories will share this mapping, so that each receive and send filter has this mapping, so that when an edit for a particular list arrives, it knows which OT manager to consult. Okay, so that's the initialization. It's more complicated because we have multiple OT managers. Okay. And the send filter, if the message is not an OT edit, OTable edit, I should say, or transformable edit, we just send it directly to the message processor. Okay, so I'm not showing you that step. Otherwise, we find the edit in that message that is being sent. Okay, in fact, we are going to be sent an edit, so we don't have to find it. The receiver is the one that has to find it. We look at the object that's being sent to us. We see whether it's an edit or not. Actually, with the send filter, so we get a message, and from that message, we have to go and extract the edit. Okay. From the edit, we extract the list. From the list, we find the OT manager. And now we do the usual stuff, which we did in causality also. We timestamp the edit, asking the OT manager to do the timestamp, okay, to compute the timestamp. And we trace a particular event which says OT list edit sent, and we send it to the message processor. So we announce to the tracer that we've sent that list edit after passing it to the OT manager. Okay, and then the message processor will further throw trace steps to say that the message actually gone or not. Okay, and after the message has been sent, we have to make sure it goes to the local buffer. So we ask this particular OT manager to store a copy of the message, okay, so that we have a copy of the timestamp, and we don't keep changing the site timestamp in this message. Okay. When it receives such an edit, if it doesn't receive a timestamped edit, then it just gives it to the message processor as before. We extract the list L and the list name L from the edit, and Now, we are at the client end, and we're going to receive a timestamp consisting of values for the remote and local sites. And what is remote for the server is local for us, and vice versa. So we're going to flip the timestamp that we received from the server. Okay. And then we are going to give, so we're going to flip the timestamp in the message, in the edit that we received. And then we're going to find the OT manager that is pertains to this list, and we ask it to transform the edit. Okay. And we pass the transform edit to the message processor, which is going to actually deliver the message. Yeah, of course. So the transformation is going to just compute the transform function we saw in class. So I'm not going to discuss how that happens. And remember, the transform function should know whether an edit is from the server or not, so that it can behave consistently at all sites. Okay. So you might, I stored the server with the timestamp edit, and you can just pass it as an argument also. Okay. And the bulk of the work is being done by the OT manager. So the OT manager, when it comes up, we sent it the username and his server argument. We create an initial timestamp. And when it is asked to timestamp, well, it does the usual stuff. It goes and increments its local count, and it takes the edit that it's been given and attaches the timestamp to it. So that's easy. Remember that our message filter came back to the OT manager after sending the message and said, please store the sent message. So it stores it in a list, and it announces a trace step saying that the message has been buffered. Okay. Later, it will be unbuffered when messages come in from the other side that are not concurrent with this message, that have timestamp greater than this message. In that case, it will get unbuffered. And this is a picture with the for the receive filter. This is when the timestamp edits are processed. They arrive from the other site. And when the message comes in, we try to find all the messages in the local buffer that are not concurrent with it, and we remove them, firing this event. And then for each concurrent edit, we do the steps we saw in great depth. We compute the two transformations and update in the local edit. We update the remote count, and then we change the site count. And these trace steps that have to do with transformed edits, they take as an argument, we'll see, a username. And that is not the name of the user who's processing this particular algorithm. It's the name of the user who issued the edit. Okay, so make sure that you communicate this information to this particular trace step, and you know which user issued it based on who the message came from. So that's something you need to put in. Okay. So username in trace step is name of user who executed the operation for local edit, the local user; for remote edit, the remote user. Exact name, not server. Okay, so it's not all edits are received from the server, but we want to give the originator to the constructor of the to the method that goes in traces. Okay. So we know now how the client OT manager works. Next question is how the how the client OT manager, send filter, and receive filter work. And now the question is, we have the complication there of having multiple clients and having to deal with multiple sequences, and dealing with both of them is complicated. And initially I was thinking I'll let you deal with only one sequence, and I might still do that in the assignment. But what I'll do next is give you an architecture that allows you to create an OT create a server end code for one sequence, and that can be extended later to multiple sequences. Okay, and the nice thing about that is that it's a very it's a composable code. You keep separate concerns in different modules. So we're going to keep basically make our filters more complicated and hierarchical. Okay, so our send filter So you may want to extend one list implementation to multiple lists, and the architecture I'll give you will allow that to happen. And that's in fact what I did. Okay, I created an implementation for one list, and then I extended that to multiple lists, and I just composed the implementation I had before. Okay, so what we're going to do is we're going to have these are the filters that assume only one list and multiple users. Okay, so each of these filters assumes multiple users. And then we're going to have a master send filter that keeps track of these filters and does the simple task of just forwarding actions to them. Okay, so going to multiple sequences is very easy, or is relatively easy if you have this architecture. Okay. So when the server is created, it must create for each sequence a server filter. Okay, so it creates the data structure to store that, and then for each list, it creates a new server filter, and it's going to pass this mapping to all of the filters so that appropriate OT managers can be found for different lists. Okay, so this is a shared data structure among that is passed to the filter. Actually, there's only one filter here, so it just goes and passes that filter, this data structure. Filter has two extra operations to know when a new user comes in and leaves. We're going to focus mainly on the new user joining. Okay, so what happens when a new user joins? Okay, for each list L, we go and tell we find the associate. This is the master server filter. So it finds the actual filter and tells it the user has joined, so that it can go and create OT managers, an OT manager for that user. Okay, and for leave we just can do the flip action, and of course we forward this the message processor also, so that these individuals filters can directly forward the message to this processor and don't have to go back through the master. Okay. So when a new message comes in, it goes and sends the message. So this also is just forwarded. Okay, so just as the join call was forwarded, the leave call is forwarded, the filter message call is forwarded to the appropriate filter created for that list. And this is the real filter, and it's got to create multiple OT managers, one for each sequence. One for each user, I'm sorry. Okay. And whenever a new user joins, it goes and basically adds to that table. Okay. And it tells the OT manager what its name is and whether it's a server or not. And this is being done in the server, so it goes and says that it is the server. Okay. And it can just give its server name here. Okay. Server send filter. So when a new message comes in, it's got to basically find the. Okay, so this is the complicated stuff now, right? So we are receiving a message from the client, okay, from some client S, okay, and we have to make sure that we flip the timestamps, okay, because what's remote for the client is local for us, and then what we're going to do is find the OT manager for that user. Okay, it's going to have all in its local buffer, all the commands issued by other users. Okay, so we're going to ask it to transform the edit we received into an OT based on the local buffer. Okay, and normally if we are the client, we would just execute the command right now, but we don't execute it. We have to go and send it out to other users. So we find all the other users. The message we get doesn't tell us who the other users are, but we know who this user is. We have a table that tells us all the users. So from that table, we find all the other users that are going to receive this. Okay. And what we have to now do is not multicast the same message to all of them. We have to now unicast a separate message to each one of these receivers that has a separate different timestamp. Okay. So we create a unicast copy of the message. So if this was OT, we create for each receiver R and OTR, and it's going to be unicast other than multicast. So what we received was a multicast message. that was supposed to be sent as such to all of them. Now we're going to create a separate copy for each user. And this is a call you need to make. We get a message which has this transform edit, into which we put the transform edit, and we know which user to go to. So we go and just make this static method call that goes and returns back to us a message that is going to be unicast to this message with this particular edit as content. Okay, so this is an API call that you need to worry about. This is not just a pseudo code algorithm or a traceable step. This is a real call. Okay. And so we haven't actually sent the message at this point. We have created a message that contains OTR. And by OTR, I mean just the raw edit, not the timestamp. Okay. So now we go and tell the OT manager for R to go and timestamp it with its timestamp. Okay. Now we are pretending to be the sender of this message. And as a sender, we have a timestamp for this particular site. So that timestamp gets incremented and attached here. And then we send that message, unicast message, through the message processor. Okay, because we got a unicast message data type here, the message processor knows that it's going to be unicast rather than multicast. And we ask this particular OT manager to now store a copy of the sent message in its buffer. Okay, and so here's a summary of the centralized algorithm. We are merging through a central server. Output is produced locally and immediately. It's not an atomic broadcast situation. And server keeps local buffer and timestamp for each client. And each client treats server as a second user and sends it each command. And instead of applying the possibly transformed command to its local state, the server sends the command to each remote client. Okay, so it computes a transformation function and then applies a timestamp on that transformed command. Okay, so this could get transformed once here, and it can get transformed a second time in the client. And client just assumes the command was executed directly by the server. Okay, so that's the view, and assuming that all clients are consistent with the server, the clients are consistent with each other also. And then I think we're assuming here that, yes, we are assuming that messages arrive in order from the other party. Okay, so you can use TCP/IP. And here's the history. The first operation transformation algorithm was published in '89 in a SIGMOD conference by Ellis and Gibbs. And they didn't transform the local operation in the buffer, and it had known problem with multiple users. Okay. Then adopted, this is the Russell paper that I keep mentioning. It transformed local operation and gave conditions for end user replicated merging, gave user conditions for the 3-user merging that we saw. And the central algorithm was invented by Nicholas Curtis et al. In '95. And they do centralized merging. And they are, in fact, implementers of live meeting. It was called Park Place at one time. And this algorithm was implemented in Google Wave and now I believe in Google Docs also.